see my full screen?
No. Now. Yes. Now, yes.
And can you see also the laser pointer?
Yes. Yes.
Okay. Good morning, everyone. I would like to thank the organizers for giving me the opportunity to present our work. The work I'm going to present is a collaboration between my group at IST Austria, Peter Krogstrup, who has provided us with the beautiful nanowires, and Fernando Penaranda, Pablo San Jose, Elsa Prada, and Ramon Aguado from Madrid. All the measurements I'm going to present are taken by Marco Valentini, so all the credit goes to him. I'm still amazed whenever I think about Andreev reflection, the fact that transport can take place when an electron coming from a normal conductor impinges on towards a superconductor with an energy below the gap. Physics becomes even more complex if now you take a conductor and you sandwich it between two superconductors, and we all know that this will lead to Andreev bound states, which are actually the microscopic mechanism which allows a Cooper pair to travel from the left superconductor to the right superconductor. So Andreev bound state physics is very fascinating, and in the past 10 years there have been beautiful experiments actually studying the physics of Andreev bound states when you have a 1D or a 0D conductor between two superconductors. In 2010, for example, Andreev bound states in carbon nanotubes have been studied. So Pilet et al. Studied by means of tunneling spectroscopy by using a leaky gate, how the Andreev bound states behave in carbon nanotubes. In 2014, Eduardo Lee showed the Zeeman splitting of Andreev bound states, and many other transport measurements have been dealing with Andreev bound states, covering nanowires, carbon nanotubes, and graphene. And in the past few years, there have been many microwave spectroscopy measurements in which they detected Andreev bound states, their splitting in the presence of magnetic field, or their zero field splitting due to spin orbit. And of course, there has been also a beautiful work in which it has been shown in 2015 that actually one can create also a qubit, the so-called Andreev qubit. And I think later on today, we are going to hear much more about it, this time in an indium arsenide nanowire. But Andreev bound states have become again additionally interesting because they can mimic all the phenomenology of Majorana bound states. And if you want to know more about it, a beautiful review has been written recently where you can read about the comparison between Andreev bound states and Majorana zero modes. So from my perspective, what is the problem why we cannot distinguish easily Andreev bound states from Majorana zero modes? So we all know the model of Oreg and Luchin, where you couple an S-wave superconductor to a semiconductor with strong spin orbit, and if you apply magnetic field, and you fulfill the condition that practically the Zeeman energy is larger than the gap, you should be able to realize Majorana zero modes at the end of the nanowire. However, in this relation, there is the chemical potential, which in principle you can tune experimentally, but the reality is we have no clue what it is. So the question then is, at what B field should Majoranas emerge? And if you go through the literature, you will see that Majoranas emerge for other different values of magnetic field. Another problem is that typically for the values that you get zero bias peaks interpreted as Majorana zero modes, the B field is already large, so the gap has become soft, and this makes the interpretation even more tricky. We believe that a solution to this problem, a way to distinguish Majoranas from Andreev bound states, come from a slightly different platform. So to use full shell hybrid aluminum indium arsenide nanowires. So these are nanowires, in the particular case, indium arsenide nanowires, which are fully covered by an aluminum shell. And obviously this needs to be done in situ. So these wires have been grown by Peter Krogstrup by in situ grow of an aluminum shell. So that means that that shell is epitaxially grown. And in this figure, you can already see that that aluminum induces a very hard gap into the semiconductor. So why is this material platform interesting? 2 years ago, well, actually 1 year ago, Luchin et al. Posted on arXiv a theory paper in which they suggested that full shell nanowires are an interesting platform for the realization of Majorana zero modes. So what you can see in figure A is a graph which shows you that if you have a strong enough spin orbit in your material and the proper chemical potential, you can end up in the topological phase. And by calculating the local density of states, a zero bias peak is appearing in the first lobe, while in the bulk of the wire, you don't see anything. Later on, Fernando Penaranda did numerical simulations of the local density of states by investigating a bit further the geometry also of the semiconductor core, whether the indium arsenide nanowire is a full cylinder or a hollow cylinder. And they found as well that under appropriate conditions, you can end up with Majorana zero modes in the first lobe. The difference between B and C is simply that in the first plot, you are in the so-called destructive little Parks regime, while here you are in the little Parks regime. Let me remind you before moving on, what is the little Parks effect? Think of a hollow cylinder which is covered by a thin superconductor and apply a perpendicular magnetic field. The superconducting current density is given by that relation. And if now you want to integrate the supercurrent density along the closed path within the superconductor, you end up with this relation. Typically, when we think about superconductors, the thickness T is very large, so Js goes to 0. So practically, typically, that term would go to 0, and we would get back the well-known to each of us flux quantization. However, if tau is now small, that term still survives, and now we have the fluxoid quantization. If you do a bit of math, you can calculate the superfluid fluid velocity, and you see that it becomes a periodic function of the flux. So if now you plot the kinetic energy, that's how it would look like for different values of the flux. And if the kinetic energy of the Cooper pair exceeds the superconducting condensation energy, superconductivity will break down. So how does this demonstrate? If you would plot the critical temperatures versus the magnetic field, you would have areas where your system is in the superconducting state, depicted here as black, and in between you would have metallic regimes, which is the so-called destructive regime. And we call the first lobe practically the 0th lobe, first lobe, and so on. And please remember, Majorana zero mode should appear as a zero bias peak in the first lobe. So I told you we think that that material platform is an ideal platform for studying the interplay between Andreev bound states and Majorana physics. Why is that so? Because here there is no fine-tuning of the electrochemical potential, and actually you cannot fine-tune it because all electric field will be fully screened by the aluminum shell. And the additional advantage is that now you know exactly at what values of magnetic field you should be looking for the Majorana zero modes. And as I'm going to show you soon, actually at that value of magnetic field, your gap is still hard. This year, the Copenhagen group reported the first measurement on this material system, and indeed they reported a zero bias peak in the first lobe, which was interpreted as a Majorana zero mode. We have done similar experiments. So that's our, on the right side, you can see the scanning electron microscopy picture, and on the left side, a 3D cartoon. So what you see in green is the indium arsenide nanowire. In red, you can see the aluminum full shell, and we have two normal contacts. We have also a side gate, but in that particular measurements I'm going to present, we have not been using it. It's actually been put to 0 volts. And the experiment I'm going to discuss, all our measurements are tunneling spectroscopy measurements. So let me just remind you what it means. So practically we have a normal metal, which is separated by a tunnel barrier from the superconductor. And by changing the bias voltage of the normal metal, we can have tunneling when, for example, the full states of the normal metal align with the empty state of the superconductor, and we can map out the local density of state of the superconductor. Important to point out is that the transparency of the tunnel barrier plays a big role, because you can either do tunneling spectroscopy or Andreev spectroscopy if your tunnel barrier becomes very transparent. And this has been beautifully demonstrated in a paper from Delft very recently, in which they have shown that by changing the potential on the tunnel gate, they can go from the tunneling spectroscopy regime to the Andreev spectroscopy regime. Now the next question is, what is the correct value of X? Being for a couple of years away from experiments performed with indium arsenide and nanowires, when we were discussing with Marco what should be the dimension of X in order to form a proper tunnel barrier, the conclusion was that we did not know. So Marco decided to make many devices. So the conclusion after measuring roughly 40 devices is that if X is below 100 nanometers, the indium arsenide behaves like a tunnel barrier, while if X is above 100 nanometers, you form a quantum dot within the tunnel barrier. We call short junction devices the devices for which X is below 100 nanometers, and with that, I'm going to start showing you our results. As I already mentioned, the first thing we need to do is to find the proper gate voltage in order to adjust the transparency of our tunnel barrier. So what you see in this measurement, we measure differential conductance while sweeping the source drain voltage and stepping the backgate voltage. And you see that around minus 19 volts, you get a very hard gap. So the difference between the subgap conductance and the conductance above the gap is about 300. So that's the regime where we are going to stay in order to do our measurements, our tunneling spectroscopy measurement. And now we fix our gate voltage and we start sweeping the magnetic field. So again, differential conductance versus bias, but now sweeping the magnetic field. And as I told you, if you now sit in the middle of the first lobe and you take a line scan, you can see that the gap is still hard. The only thing which has changed is that the gap has become slightly smaller. If now you check this measurement, obviously you observe that there is no zero bias peak. Please remember that according to theory, if we would have Majorana zero modes in this system, we should see a zero bias peak in the first lobe. We have investigated many short junction devices, and here I show you an overview of 8 other devices. In the top right of each device, I'm giving the dimension of X, of the tunnel barrier. And on the left side, you can see the measurement we have done in order to find the regime for which we will be doing tunneling spectroscopy. And on the right side, we have fixed our backgate voltage and we are sweeping bias versus magnetic field. What you can see is that in none of the measurement, we see any zero bias peak. So we have no indication of Majorana zero modes. If you take a careful look to these plots, you will see that there are a slight difference between the measurements. So for example, the height of the lobes is slightly different. Also, the distance of the lobes is a bit different. So how can we understand that? Going back to Landau-Ginzburg, there is a theoretical formula which allows us to extract the ratio between the critical temperature for each lobe versus the flux, where psi is the d gamma function and alpha is the pair breaking parameter, which relates to the coherence length, to the radius of the nanowire, and the thickness of the superconducting shell. Effectively, by using these formulas, now you can plot TC versus magnetic field, and you can really see the little Parks effect. But if you would fix the diameter of your nanowire, the radius, the coherence length, and you would change the thickness of your superconductor, you can see that the height of the lobes changes. On the other hand, if you fix the thickness of the superconductor and coherence length and you change the radius, you can shift their position. So based on such a type of analysis, we take these 8 devices, we analyze them, and what you can see that actually, as it is expected, they don't have all the same parameters. We are doing experiments, so the wires are not always of the same thickness depending on where you are doing your device along the nanowire. So practically, you can see that we have a spread in the thickness of the superconductor, on the radius, and on the coherence length. So, as I told you, no Majorana zero mode at short junction devices. However, all the devices we have been studying were in the destructive little Parks regime. So could it be that in order to see Majorana zero modes, we need to go to the weak little Parks? So practically, if you shrink your thickness of your superconductor quite a bit, you will end up into a regime where superconductivity never gets completely destroyed. We fabricated also devices of this type. And here I show you just one measurement in the weak little Park regime, where now the tunnel, the junction length is 50 nanometers, differential conductance versus bias and magnetic field, beautiful weak little Park regime, but no zero bias peak. So then the question is, why don't we see Majoranas? According to both theory papers, it is clear that such a material system should allow us to realize Majorana zero modes. And we have 3 kind of possible explanations. The one question is the spin orbit not strong enough of our intrinsic nanowire? If you take a look at plot A, in order that you reach the topological phase, your alpha, your spin orbit constant needs to be higher than a certain value. So can it be that our nanowire has not strong enough spin orbit? Or can it be that actually it had strong enough spin orbit, but the superconductor has renormalized the semiconductor properties? Or have we simply used wrong wire dimensions? Well, at the moment, we don't have an answer to these points, but we are currently trying to go step by step through each of these 3 assumptions. So then let's move to long junction devices. So now within our X, we are going to host a quantum dot. And as it is known, the physics becomes very complex once you proximitize a quantum dot with a superconductor, and then you do tunneling spectroscopy measurements. So for example, if you have a quantum dot and you have an odd number of carriers, then depending on the ratio between gamma S and U, you can be either in the doublet ground state or in the singlet ground state. And in the particular case of our experiment, since U in our case, which is the Coulomb energy, is much larger than the superconducting gap, our singlets are UCR singlets, about which Katharina Franke gave a very nice talk yesterday afternoon. So let's see how our devices behave when we have a quantum dot in the tunnel junction. We measure differential conductance versus bias and backgate voltage, and you can see beautiful Andreev bound states. So you can see the characteristic loop-like feature, which is a fingerprint of a doublet ground state. And we will focus first in this regime. So that's the same plot, but at zero magnetic field, zoomed in. If now you crank up the magnetic field and we focus again in the doublet ground state, what you can observe is that the energy of the Andreev bound state has increased. How can we understand it? If we have a doublet ground state and you crank up the magnetic field, the doublet ground state splits. And since in our measurements, we measured excitation from the ground state to the excited state, zeta is increasing with magnetic field. So let's And that's in agreement with the measurement which Eduardo Lee has done back in 2014, which are so-called the Zeeman-driven Andreev bound state evolution. So in the doublet state, you can see very nicely that also in his measurement, the Andreev bound states go up in energy. So let's fix now our gate voltage to the green position, and let's measure again the differential conductance versus bias and magnetic field. And we can observe now how the Andreev bound states evolve. I already showed you that if you take the line scan here, you will see that the Andreev bound states are lying at higher energy compared to zero field. And if now you take line scans in the destructive regime, what you will see is you will see this split peak, which is nothing else than the Condo split peak. And in order to confirm that, we did a temperature dependent measurement. So the Condo peak disappears a bit below 3 Kelvin. So it is interesting to note that in the 0th lobe and in the first lobe, where we have a hard gap, we can see just Andreev bound states. When we kill superconductivity, we see just the Condo effect. But in the second lobe, where we have a soft gap, we can actually distinguish both Andreev bound states and Condo. We use now the Condo effect in order to extract the G factor of our nanowire. So if you go much higher to much higher magnetic fields where practically superconductivity is dead, so if you sweep your magnetic field from 600 to 800, you can follow the evolution of the Condo peak as it splits, and from there we can extract a G factor of about 10. So let's move now to the singlet ground state. And now we are going to focus into that regime. We do the same game. We crank up the magnetic field to 110 millitesla. Now we see a splitting of our Andreev bound state. How do we understand that? Again, if we go to the picture I showed you before, but now we have the singlet as a ground state, the doublet splits, and now we are able to resolve zeta up and zeta down. This is similar to what Eduardo reported for Zeeman-driven Andreev bound state evolution. So you see his graph at zero magnetic field, and while he cranks up the magnetic field, you can see the beautiful splitting. And as you see, now if you have a singlet ground state, you could have, well, you will have eventually a zero bias peak when the singlet and the doublet will merge. Indeed, if you now fix your gate voltage at the blue position and you measure differential conductance versus bias and magnetic field, you can see the evolution of the Andreev bound states, and we end up with a zero bias peak in the second lobe, and that can be beautifully seen in the line scan. So if you take line scans in the first lobe, you start with 4 peaks. The middle ones approach, merge to create a zero bias peak, while the outer ones move away. And throughout the second lobe, you have a zero bias peak. So it means that before I move on, let me just tell you that from the splitting of zeta up, from the difference of zeta up and z down, we can extract the G factor. And we extract again a G factor of 10, which makes sense because it's the same device. So it means that now, depending on the backgate voltage, we can tune the position of our zero bias peak. So if now we go, we change our gate voltage in this range, you can see that either you don't get any zero bias peak within the first 2 lobes, or if you go to the yellow position, you can actually tune your zero bias peak to be at the first lobe. The question now is, would it be possible to have a zero bias peak appearing in the first lobe if your Andreev bound states would be hidden in the gap? The reason why you can get here a zero bias peak is simply because you need just a very small magnetic field to make them merging. In a first glance, you would say it is not possible if your Andreev bound states are hidden in the gap to get a zero bias peak, because simply if that would be the gap, 200 microelectron volt, the condition in order that, that you get a zero bias peak in the first lobe, which is roughly 100 millitesla, would be that. And this would imply that your nanowires would need to have a G factor larger than 50. And we have demonstrated that our nanowires have a G factor of 10. So let's move on to some other long junction devices, which, however, show zero bias peaks in the first lobe. So if now we look at zero magnetic field to see if there are subgap states, here obviously there seems to be still a subgap state. Here you can probably guess there is a shoulder, that maybe there is something, but in that device, actually just from that line trace, you would not guess that there is any subgap state there. So let's take a closer look to each of these three devices. Let's start with device C. And you see in the first lobe a zero bias peak, which actually is splitting as you crank up the magnetic field, so that you can see here in the measurement of the differential conductance versus the magnetic field. You start with a beautiful zero bias peak, which splits as you crank up the magnetic field. So let's take a look how that device looks like if we start changing the backgate voltage. So what I show you here is a zero magnetic field measurement, where we sweep the bias versus the backgate voltage. And the dashed pink line is the position for which this plot has been taken. So obviously, also this device has Andreev bound states. And if now we put a magnetic field of 110 millitesla, which is in the center of the first lobe, and we measure again the differential conductance versus bias and gate voltage, you can see that the zero bias peak extends for actually a bit more than 100 millivolts. However, if you take a close look, you will see that very close here, there are two peaks which merge together and then separate again, telling you that also that is an Andreev bound state. As a verification, if now you would take, you would fix your gate voltage at minus 1.8, that is the plot you would get, so no zero bias peak. Please remember that if the origin would be Majorana's, by changing the backgate voltage, nothing should change, because we are not able to change the electrochemical potential in our wires. So if we would have a Majorana, it should not depend on the backgate voltage. Let's move on to device D, which shows again a zero bias peak. We do the same game. We measure the differential conductance versus bias and backgate voltage at zero magnetic field. And it's obvious that also in this device, we have actually quite some Andreev bound state features, which we don't fully understand. And if you take now the same plot like that, but in magnetic field of 108 millitesla, which now corresponds to the center of the first lobe, again, you can find positions like the blue one, where you would have a zero bias peak, and the majority of the positions would not allow you to see a zero bias peak. And let me finish with our last device, device E, which shows actually not just a zero bias peak, but multiple lines, additional peaks appearing at subgap voltages. If now we take at zero magnetic field the differential conductance measurement versus bias and backgate voltage, you see again that there are plenty of Andreev bound states. Interestingly, in this device, it seems actually that we have more than one pair of Andreev bound states. And if now we fix our magnetic field at 123 millitesla, which is at the center of the first lobe, and we measure conductance versus bias and backgate voltage, you can see that the zero bias peak extends over a certain range, then it disappears. And you can see also all these additional subgap states, which we believe must be due to the fact that we have more than one pairs of Andreev bound state. So the question now is, how is it possible? I told you that, that if we have an Andreev bound state hidden in the gap, the condition in order that you see a zero bias peak would be that, which would imply that we would need a G factor larger than 50, which definitely we have not in our system. And in my last slide, I will just glance over theory results, which afterwards Fernando Penaranda will explain. So if you start with a superconducting Anderson model and you consider the constant pairing case, which is not our case, so that would be in some sense for a nanowire with a half shell, where when you sweep the magnetic field in a small range of magnetic fields, the gap is not modulated very much. What you can see here is the numerical density of states. So these are the Andreev bound states. The green lines would be the pure Zeeman evolution. And what you see in red are the poles of the green function for the superconducting Anderson model. So you already see that there is a deviation between the purely Zeeman regime and the superconducting Anderson model, in which you need to take into account also that now you have a coupling to the superconductor. But where everything becomes much more complex is when now you allow delta to be a function of the flux. So the picture completely changes, and actually experimentally you would not be able to understand that were Andreev bound states. So you can see that the position where the zero bias peak has emerged has completely changed. And due to the modulation of the gap with the flux, practically you cannot distinguish the splitting of Andreev bound states. So you would see one blurred subgap feature or barely a feature appearing at delta, and then you would get a zero bias peak in the first lobe. But more about it, you will hear in Fernando's talk, who is going to give you much more insight into the theory behind it. And with that, I'm already at the end of my talk. I hope that I managed to convince you that hybrid full shell indium arsenide devices are very interesting for studying fundamental physics. We have fabricated short junction devices, which in my opinion should be the ideal way in order to study Majoranas. We have not seen any signature of Majorana zero modes. When we allow a quantum dot to form in the tunnel junction, we can see Andreev bound states, which can perfectly mimic Majorana zero modes. With that, I end my talk. I would like to thank the funding agency for supporting us and you for listening to me. Thank you very much.
Thanks a lot, Georgios, for this very nice and clear presentation. I think there are already questions from the audience, and you have been perfectly on time, so we have like 5 minutes for questions. So if you don't mind, because I think it's better to read the questions and not to give the microphone to each one, because then we can have more time. Okay. So from Francesco Borsoi, he says, good morning, nice data. Have you observed enhanced conductance due to Andreev reflections in the open regime for certain junction sizes? So
Marco tried to move from tunneling spectroscopy to Andreev spectroscopy, and the conductance we are getting is always much lower. So it seems the transparency of our contacts is not good enough. So we don't even get 2e squared over h.
Mm. Okay, it's transparency. Okay, then from Cyril, in Luchin's paper, the zero bias peak is there only if the chemical potential is right. Isn't it the reason why you do not see it?
Well, that could be one of the reasons that the particular nanowire sample we are working on has the chemical potential in the wrong position. That I agree. That's one of the three options which we need to find out whether it's that particular material combination which does not allow you to see it. Yes, could be the reason.
Okay. So the theory is also changing the chemical potential. That's why it shows it. Okay.
And we cannot change it.
Yeah. Okay. So Elsa, okay, Elsa is answering. Chemical potential has to be right, and you cannot tune it. Okay, she's already saying what you said. However, if you calculate the phase diagram, you get Majoranas in roughly half of the meat of it, meaning that you might not have Majoranas in some devices, but you should find them in others. Okay, perfect. Alexander Kopasov, did you try to estimate the number of transverse channels in the core in your devices? Can you say something about the Fermi level pinning?
No, we have not estimated the number of subbands. That I cannot tell you.
Okay. Okay. Lawrence, is localization along the prism edge forming 1D wires what may interfere with each other a relevant thing?
Sorry, can you repeat?
I have to understand the question also myself. Is localization along the prism edges forming 1D wires that may interfere with each other a relevant thing? He is asking whether localization along the prism edges is a relevant thing. Along the prism edges, so the edges of the prism of the nanowires. So I think this is more a question for the theory, perhaps.
I think according to the paper of Fernando, if I understand, depending whether your let's say wave function pins at the interface of aluminum and indium arsenide, which would be the case of their hollow semiconductor, you would see a different spectrum, but still you should see Majorana zero modes.
Yes.
Yeah, because I mean the calculation they have was for cylindrical, and he's asking if for a prism. Okay, but I think there is theory for prisms also, no? Well,
for a prism, yes. Yeah. I think it should work for both.
Okay. And Juan Carlos Estrada. There is a zero bias conductance deep inside of a Siemens split condo feature.
Yes.
It also shows in some of the finite field measurements when the superconducting gap becomes soft. Could you comment on the possible origin of that?
Okay. So I will speculate. So what I'm going to tell you is a heavy speculation. So I think that's what the question is. For example, if you sit in the first lobe for one device and you measure again differential conductance versus bias and backgate voltage, depending where you sit again with your backgate voltage, if you are really deep into the tunneling spectroscopy regime, you just see a hard gap. But if you tune your backgate, indeed you can see the evolution of this zero bias deep. What we found in the literature is that for disordered superconductors, which I show here on the right side, so the group of Claude Chapelier and Grenoble, they have done tunneling spectroscopy by means of STM. So they seem to see a similar dip. So the heavy speculation is whether while we do etching, we create disorder into the aluminum. But as I say, take this as a heavy speculation. I would be happy if a theorist could provide me with an answer.
Okay, perfect. Thank you, George. Thanks the audience for the questions. And now let's move to the next talk. So we are then in time. And Fernando, please. And thanks, George, again for this nice presentation. Fernando.
Okay, So let me see if I can.
So Fernando
okay.
is, yeah, okay, is presenting the theory part for this flux tunable Andreev states work. Thank you.
Okay, so hello to everybody, and thank you, Alfredo, and the organizers for allowing me to present this work on Andreev bound states in hybrid functional nanowires. This theoretical study was developed by the Madrid part of the collaboration and complements the experimental results obtained by the IST and Copenhagen groups, as previously explained by Jorgos in his talk. So after Jorgos' talk, he already introduced the basic properties of these functional nanowires. But in order to motivate our work, let me just introduce the key concepts. So semiconducting nanowires with strong reciprocal coupling in the presence of a longitudinal magnetic field and proximity to an superconductor were proposed as a physical realization of a B-wave topological superconductor that can host Majorana modes on its edges. However, unambiguous signatures of these topological and non-trivial states have so far been elusive due to the fact that Andreev bound states may mimic all the subgap phenomenology in tunneling conductance associated to Majorana modes. So a recent proposal by Saulis Vadiekinas and collaborators named the pulsion nanowires also predict the existence of Majorana modes in extended flux regions in integer lobes. The difference between these nanowires is that now the superconducting shell fully coats the semiconducting nanowires, and there is no longer a requirement for high magnetic fields, which place them as a promising platform to finally observe them. So then the question arises, do they suffer the same problem due to the presence of trivial states? So, well, in Jorgos' talk, we have already seen how quantum dot formation within the tunneling region could lead to subgap states, and they crucially disappear in long junctions below a typical threshold of 100 nanometers, whereas for larger regions, we can see a very clean and clear signatures of quantum dot-like subgap states. So in this talk, we will introduce a minimal model that helps us to understand the nature of the subgap excitations found. We will also describe the phase diagram of the system in different coupling regimes, finding an unusual flux-induced quantum phase transitions. And finally, we will also study the intriguing evolution of Andreev bound states with magnetic field. So as we already see, when we have superconducting cylinders threaded by a magnetic field, the order parameters have a subperiodic modulation as a function of the applied flux. This is due to the single value character of the complex order parameter phi. Sorry. However, deviations from this behavior depicted in this graph as a black dashed line were predicted to exist for radius and for cylinders with radius and thickness much lower than the coherence length, as it is the experimental regime. In those cases, the superconducting currents circulating around the shell induces an additional pair breaking mechanism that leads to the full destruction of superconductivity in finite flux regions around half-integer fluxes. This was recently observed in this experimental work, also by Saulis Vadiekinas et al., in which at zero temperature, we clearly see how metallic and superconducting phases oscillates with the applied in-plane field. So in order to describe the experimental setup, we will use the following Hamiltonian as a sum of the following terms, Hamiltonian describing a two-level system with Coulomb interaction and charging energy U, which describes the quantum dot forming in the tunnel region. Then a Hamiltonian for the normal lead, another BCS Hamiltonian that describes the full shell nanowire. Note that here the BCS gap delta is dependent on the applied flux due to the destructive little Parks effect. And finally, we have two tunneling Hamiltonians from the quantum dot states to the normal and superconducting leads, which upon integration of the fermionic paths in both leads gives rise to the two tunneling rates, gamma n and gamma s. So this is the standard formulation of the impurity Anderson model coupled to normal and superconducting leads and with destructive little Parks effect. So a full treatment of the problem in principle requires to take into account electron-electron correlations. However, the Coulomb blockade regime is well captured by means of a Hartree-Fock Pavlov approximation, which, as we will see, it provides a good agreement with the experimental data away from the Condo regime. So from the poles of the retarded Green's functions, we can derive the energy of the Andreev bound states, which reads like this. And note here that all tilde quantities must be determined self-consistently because they depend on the occupation of the dot levels. So despite its simplicity, this model correctly captures the interplay between two competing mechanisms, which are the Coulomb interaction that favors an odd occupation in the dot with a doublet ground state, and Andreev processes that favors, on the other hand, a singlet ground state, whose physical nature will depend on the ratio of delta over U, as we will see. So we can start looking at the large delta over U approximation. In this regime, the superconducting just induces superconducting correlations in the dot in such a way that if we start in an odd occupied Coulomb diamond, the first excited state will be singlets formed by combinations of states with even occupation. So phase diagram, energy of the dot versus gamma s coupled to the superconductor looks like this. We clearly see a doublet dome, which is surrounded by a singlet phase. So, as a side note, a more accurate description of this problem, this limit, can be achieved by means of the finite delta perturbation theory or by numerical normalization group. However, in the following, we will focus on the other regime where U is much larger than delta, which, as shown in the experimental data, this is the experimental regime in which we are away from the destructive little Parks regions. So in this case, the singlets are not formed by mixing of occupations of doubly and empty occupied states, as it was the case before, since these states would lie well above the gap due to the large charging energy. What we have instead are bound states formed by the coupling of the impaired spin to the quasiparticles in the superconductor. So if we take the large U limit in the previously derived formula for the Andreev bound states and evaluate it at the electron hole symmetric point, we get to the following expression for the energies of the subgap Andreev bound states as a function of with dependency on the magnetic field. So we can plot this result on top of the experimental data and find very good agreement without additional fitting parameters. So we can, if we reformulate the original problem as a Condo cotunnel Hamiltonian coupled to superconducting and normal leads, we can get more insight on the physics of the problem. This can be done by means of a Schrieffer-Wolff transformation, which traces out the high energy sector of the Anderson model. So now the Hamiltonian reads like this, where h of j is the Condo Hamiltonian. Here j describes the exchange coupling constant between the single impurity in the dot and the quasi-particles in the leads, which upon a semi-classical approximation, which is valid in the small j regime, leads us to exactly the same formula as the one derived above in the language of the Anderson model. This is the standard expression for the energies of UC various enough states, now written in the language of the Condo model. So taking advantage of this alternative description, we can express J as a function of the Anderson model parameters, and also we can get an estimation of the Condo temperature of the problem at which it becomes non-perturbative in J. So the physical picture at shear temperature will be the following. When the Condo temperature times Boltzmann constant is the lowest energy scale of the problem, the ground state is just a free local spin, and the first excitations are UC version of singlets described by this expression. However, when we go to a regime in which KBTK is of the order of the pairing, and the ground state changes due to the full screening of the local spin. If the gap is exactly 0, this gives rise to Condo singlets, and if it is finite, it gives rise to UC version of singlets. So there are essentially two different ways to reach this Condo regime. The first is by increasing the Condo temperature, which can be done by increasing gamma S, the coupling to the superconductor, as it was done by Eduardo Lee et al. In this paper. And another possible way to do that is to destroy superconductivity for a finite exchange coupling constant. So the destructive little Parks effect induces flux-induced quantum phase transitions, since it determines the availability of the screen electrons to form Condo singlets. So if we look at this experimental data, here we can start at a doublet phase and go to a Condo singlet and go back to a doublet ground state as we cross a flux region with full suppression of superconductivity. So the line cuts previously shown by Jokos clearly indicates this formation of Condo singlets. And I'd like to note that in the soft-cap region, it is very interesting because both UC Arsenov and Condo physics coexist, as we can see two different peaks in the line cuts. So in order to show the agreement between our theory and the experiment, we show 3 different singlet doublet transitions, which occurs at different fluxes due to the fact that they are the experiment is done on its panel on a different backgate voltage. So the theoretical simulations correctly captures the subgap phenomenology, which is valid away from the Condo regime, that is the full superconducting regions. So the last panel, it is interesting because it shows an extended zero bias peak in an outer lobe. So to get a better understanding of this behavior, we plot 2 more DIDV simulations with the pole structure superimposed in red in a different coupling regime with larger gamma S. So on the left, the little Parks effect is off. It means that the gap is constant. And in green, we plot the expected behavior for a purely Zeeman-driven regime. What we see is that as we increase the flux, the energies of the Andreev on the states crosses at a given flux value and then disperse. This behavior is completely different to what It happens when the little particle effect is turned on. In this case, the Andreev found states become flattened in the magnetic field, and in such a way that the features of the crossing may be unresolvable within the experimental broadening. So it also leads to extended zero bias peaks throughout the first lobe. This closely resembles what it is actually found in the experiment, as it was shown before by Jokos. So to conclude, we have identified the nature of the subgap excitations as UC-original states, which is in good agreement with the experiment. We have also studied the phase diagram of the system, and we have found these flux-mediated doublets to Condo Singlet quantum phase transition induced by the destructive little parts. And finally, we have also showed that Andreev found states, which results from this quantum dot formation in the tunneling region, can give also rise to extended zero bias peaks in odd lobes. So with that, I conclude. Thank you for your attention.
Thank you very much, Fernando, for this nice work. And well, we have time for one or two short questions. You may either raise your hand or write it in the chat. Well, if there are no questions, maybe I ask one short question. Can you tell us what are the fitting parameters when you compare with the experiment?
Okay, in this, do you refer to these graphs?
Yeah, these ones. Yes.
Exactly. Well, gamma S is the coupling to the superconductor, as well as gamma N, which introduces finite broadening, fitting parameters, but also the radius and thickness of the wires has to be determined by these little Parks formula, but the rest are well-known, parameters extracted from the experiment, the charging energy. Yeah.
But essentially, the condition to have the zero bias peak at the first lobe is only the size of the gap, no? Essentially, compared to.
Well, essentially, you have to also tune the position of the dot levels, the dot's energy, in order to have these Andreev found states starting the appropriate energy at zero flux, so they can develop this extended zero bias peak. Yeah.
Okay, thank you very much, Fernando.
Okay.
And now we go to the next talk, which is going to be by Christian Schonenberger from Basel University. Hi, Christian. He's going to talk about spectroscopy of the superconducting proximity effect in semiconducting nanowires. And you can start whenever you want.
Can you see my screen?
Yes.
Is it full screen? Is it okay?
Yes.
Presentation.
Yes, perfect.
All right.
Thank you.
So let's get a laser. Okay, so thank you very much, Alfredo, for the introduction. And let me start the timer here. Sorry, so let me stay on time. Okay, so thanks for all organizing this conference during these very difficult times. So that's although we are all remote, it's very nice to have this opportunity to speak here. The work I'm going to talk about is spectroscopy on semiconducting nanowires using built-in quantum dots, and you see a lot of people here on this front picture. But the work I probably will be able to tell you during this short time is mostly been done by the first row of people, particularly Christian Jünger, Andreas Baumgartner, Raphaël Delagrange, Denis Chevalier, and all the others are also contributing, kind of other people using semiconductor nanowires in my group. And then there are contributions, which we acknowledge here from our own theory, from Jelena Klinovaya and Daniel Loss. So tunneling spectroscopy, you know, I mean, that's probably the standard thing which is done today when one is searching for Majorana-like bound states. And most often these tunnel barriers are generated in nanowires using side gates. But what we really need, we want, as emphasized before this morning already, so we need to have tunnel barriers which couple weakly so that you can really get large suppression also in the superconducting state. The barrier should be, the location of the barrier should very well be known, and it should be reproducible. And some of these tunnel barriers induce the side gates, in particular if they're not very, you know, very close or very close to the nanowire, they can induce soft barriers and then give rise to Andreev bound states. So we will using, instead of side gates now in our experiments, built-in quantum dots. And you can use these built-in quantum dots in two ways. So the first way, you use them as tunnel barriers. So if you put your resonance state away from the Fermi energy, then you're in co-tunneling regime, in Coulomb blockade, and then essentially it's just a good tunnel barrier. But you could also go to resonance, and then you can use the quantum dot as an energy filter to do spectroscopy. And there are also some theories which propose to use quantum dots coupled to Majorana bound states, for example, for Majorana qubit readout. Okay, so that interesting paper here, which still, I mean, is still question mark for me, is this often cited paper on the hard gap, which we have also seen this morning already. So where it is said that if you use aluminum-coated nanowires, indium nanowires, where the aluminum is grown ex situ, this is the red curve, then the gap suppression which is found is kind of soft. And if you use this in situ grown aluminum, which grows epitaxially onto the indium arsenide, then you get much harder gaps. So it's quite interesting. But for me, this is kind of also limiting our own possibilities in my lab. So, you know, we get nanowires, and if you want to put aluminum at different places in some, you know, scaling up structures, you want to be available. You maybe want to put this aluminum on the wires yourself in your lab. And if this is not possible, I mean, this is kind of like, it means that we always have to get epitaxial in situ grown aluminum. So for me, it's still a question why, you know, soft gap appears, what's the origin of the sub gap, and most importantly, eventually, it's maybe not so important whether the suppression is strong in the superconducting state here. Most important is whether the parity will be conserved. So even if, you know, it could be that there is a soft gap, but if you can prove the parity is still conserved, then it is not really an issue. Okay, so here's a sketch of how you know, Majorana nanowire could look like in the way when you evaporate superconductor afterwards. Then you have a section of nanowire, some lengths, maybe this tunnel barrier yellow on the left, the tunnel barrier on the right, and we evaporate the superconductor using an adhesion layer like titanium and palladium. And then the problem is actually like this: you induce first superconductivity maybe in the, you know, in this adhesion layer, but this adhesion layer on its own can have an inverse proximity effect and suppress the gap in the region of the nanowire. And then you want to induce superconductivity in the bottom part. And you know, there are many issues which can happen here. As mentioned, the interface could be not good. Maybe this palladium layer is too thick, inverse proximity effect is strong, and this may lead, and then this will actually lead to pure Andreev reflection at this interface here in the nanowire, and that may produce a soft gap in the system. There's other factors that can play a role in our experiment. So if you evaporate superconductors, which are not very long, let's say this is a contact length, maybe 300 nanometer, you can still tunnel essentially through the superconductor. You know, you can co-tunnel through the superconductor, and that can also give rise to it looks then, you know, you can just go through the superconductor to the normal lead, and then you see normal density of state, which is not due. I mean, there's nothing to do with a real problem soft gap. But there are other things like pair breaking effects, finite temperature, and so on. And I mean, the interesting thing is that this issue of soft gap started when people were making the first tunnel barriers, and they saw soft gaps, and it's still with us today. All right, it was a pretty long introduction, so let me show you just the nanowires we are using. So we are using two kind of nanowires. So the first ones, which I show this picture, are coming from the group of Lucia Sorba in Pisa, and they are generally, you see the quantum, you see the tunnel barriers here in darker gray, and essentially they are made by using indium phosphide as a tunnel barrier. And the indium phosphide has a larger gap than indium arsenide, and in the conduction band there's a band offset of around 0.4 electron volt, which means it's quite large as compared to low temperature energy scales. So you can make quantum dots with very strong confinement potential, quite locally, well defined. And here below you see a measurement of Coulomb blockade diamonds using these quantum dots. And it looks pretty stable, actually, very nice spectra, but there are some switches. For example, here is a gate switch. Here's something happening, and then more. I mean, here's a switch as well. So from time to time, there are also gate switches in these wires, but they're typically much more stable than quantum dots we have been making before using gates. There is another flavor of quantum dots. These nanowires are made in the lab in Lund by the group grown by Kimberly Dick's group and Dunning. We do measurements together with them in collaboration with Klaas Tillander and Lehmann also, and obviously Malin Nielsen is also now with us. She was coming from the lab of Lund. And these nanowires, here the quantum dots are formed by by change of the crystal structure in indium arsenide. So the nanowires are basically zinc blende nanowires. So they're typically a bit large in diameter, maybe 100 nanometer or so. And then the Lund people are able to change the crystal phase during growth. So they can switch from zinc blende to woodside. And the woodside has a smaller band gap than the zinc, the other way around. The woodside has a bigger band gap than zinc blende and gives about the potential step in the conduction band of around 100 millielectron volt. So this is a smaller barrier, means the woodside barrier has to be a bit longer. So typically growth of this length is about 20 nanometer. So this object is longer than what you have seen before. It's maybe 50, 60 nanometer long. So you can, it's also hard to see because it's the same material in a normal electron microscope, just the orientation, that's just the order of the atoms changed in the crystal. So these are even better quantum dots, as you can see here. This is a measurement where you see Coulomb blockade diamonds with normal metal contacts and large addition energies on millivolt scale, cool charging energy also 5 millivolt or so, and very, very stable, no switches. And you see many lines here outside the Coulomb blockade region, and most of these are not the excitations of the dot. They're actually structures from the lead. So maybe this picture here, when you think you have the quantum dot here, we connect it with some long leads, maybe a few hundred nanometer long, and then there are bound states. You know, if the crystals are very good, then you have ballistic transport here, and then bound states form. We call them lead states, and all these lead states you see spectral features in these measurements. So in this particular quantum dot, I stay now with the quantum dots from Lund. What we have is, in our case, just one gate, one back gate. And when you change the back gate, you change the level, the quantum dot level, but you also change the doping in the leads. So let's see, you know, if you go to large gating, then the Fermi level goes up above the conduction band, and this would be the Fermi level in the lead. And now you can also move the dot around. And you should just remember that we also change the chemical potential in the lead. And if you go to large doping, then what you will reduce is the barrier height. And if the barrier height comes down, then the coupling from the dot state, you know, becomes larger. The lifetime of the dot states becomes shorter and makes the level broader. So the level broadening, which is measured here, this gamma, will increase with gate voltage. So this is the doping axis, gate voltage. There are more electrons here, and then the barrier comes, you know, gets smaller, and gamma gets larger. And this is a range we can use these systems from about a few tens of micro eV to up to a few millielectron volt. So now this is the interesting experiment for this session here. So here we have a quantum dot generated by this crystal phase control in the marsenite. It's a superconductor, is aluminum, and it's placed on purpose some distance away to study how the gap or how proximity effect is evolving in this lead section when you change the doping of the nanowire. So if you go to negative voltages here, it's not shown, then there's pinch off. There are no carriers in the backgate, but so, from few hundred millielectron volt onwards in backgate, then there will be, the Fermi level will be above the conduction band edge, and you see transport. And now what we are looking at, this is a low temperature in the dilution refrigerator. So you see the Coulomb blockade diamonds of the quantum dot, and what you want to see is maybe some, some feature appearing where the levels cross. And you can see here, well, don't see anything. So there's no signature of superconductivity. Then you go a bit higher in gate voltage, higher doping. Unfortunately, this is a bit low resolution, but let's go just immediately very large, like 6-7 volt. And now if you look inside here, you see something appearing on the scale of 100 micro EV. This is the gap. So we're going to look into this a bit more in detail. And what we do next, we're going to look in the co-tunneling regime. This is shown here. So this is now a zoom in. This is a scale 500 micro EV. We look the function of gate voltage again, and the blue lines is a spectrum taken in the middle of the Coulomb blockade diamond. So this is co-tunneling regime. You just see noise here at low bias, low gate voltage. If you go to larger gate voltage, then at some point there is some feature appearing, right? Some kind of a gap. And if you go to large voltage like 6, then it's a nice gap, which has the right size of order 150 micro EV. And if you now plot this, as one should do, the conductance against the normal state conductance, then you see there is some suppression, but the suppression is very weak. It's factor of 2 suppression. This would be, we should call this a soft gap, and it's even the softness doesn't change much with the gate voltage. So here we have a soft gap, and here will also be the question, why is it soft? So you can also do the other thing. You can look at the resonance point, as I said, the Coulomb blockade resonance, and now this is the other way around. So maybe you start here. This is low backgate voltage, then we go to here, and then we go here, and then here. Okay, so if you start at low backgate voltage, you see this Coulomb blockade resonances. This is the experiment, this is the model. So you see this just crossing, maybe, you don't seem to see much of a superconductor, but here on this side, you see there's the tips of the Coulomb blockade diamonds are shifted apart, obviously, right? This is kind of obvious. And in the model, it's a bit clearer, there's less noise, obviously, but maybe most clear it's here. Then you see that the Coulomb blockade tips here, they are shifted. They're shifted Coulomb blockade tips. And there's also, this additional line going through the gap. Now, if you have never seen this, I should maybe show you this plot quickly. So assume you have an NS junction with a quantum dot, and let's assume there's only quasi-particle tunneling possible. We have a very good gap. Then what will happen is that instead of the Coulomb blockade diamonds will touch at zero bias, they will be shifted away by plus minus delta, and this is what you would expect to see. So this is the blue part. This would be the onset of quasi-particle tunneling, in this region, and this in this region here. And in DIDV, you would see these lines. Now, if there's a soft gap, if there's normal state, if there's a density of state in the gap, then you will still, the usual Coulomb blockade diamonds will be this, right? This dashed part. Then you see both the dash part and the bold part. And that's what you exactly see here, right? This is exactly what I explained. And so you see there's a gap here of right order, but there seem to be similar density of state in the gap as outside. So that's why this line in the middle has the same intensity in this plot. Now, if you go further in gate voltage, now this goes to 6 volt upwards, you see the gap still, doesn't change much in size. It just starts to blur here, but this is because now the levels get the lifetime of the level of the system gets very short, and the level broadened quite a bit, and that's why it looks so fuzzy. So, okay, anyway, we can explain this quite well. We see an induced gap of close to the aluminum gap, but it's always soft. Okay, so interesting thing is that actually the gap appears at some threshold, and then the gap maybe you see first in proximity a bit smaller gap, but then it goes up very quickly, and then it stays essentially constant. And the way we interpreted this transition from a gap which is opening or Andreev bound state that that are smaller than the gap is by saying that on the left side, the length of the wire, the length of the lead is longer than sort of the coherence length, and so you are in a long junction limit here, while on this side you're going to change into the short junction limit. And the understanding of this is very simple, because if you change the backgate voltage, your Fermi level goes up, and if you're just above the conduction band minimum, you are very low carrier density, and the Fermi velocity is then very low. And if the Fermi velocity is very small, the essential coherence length is short, and you are, and the length of the physical length of the wire is longer than the coherence length, and then you are in essentially the long junction limit, where Andreev bound state can fill the gap, and it gives sort of like you eventually don't see a gap at all, and then all of a sudden it comes up, and then in this region there is essentially only a pair of Andreev bound states left, which is pushed to the gap edge, and that's why we see an apparent gap which is very close to the aluminum gap. Doesn't explain why it's soft, but I mean, it explains this sharp onset, and this can also be simulated quite well by theory. Now let me go over the last 2 minutes to this sample. So this is one which has now two superconductors, one on the left and one on the right. Again, the quantum dot is positioned asymmetrically, so there's a short lead on the left and a long lead on the right. But now it's S dot S. And now again, we will look at how the Andreev bound state, how the superconductivity is induced in these two sections. And let's start at low bias voltage first. Sorry, gate voltage is lower carrier density, and that's how the spectrum look like. I mean, there's 3 experiments a bit higher up, a little bit, in fact of 2 higher up in gate voltage, but that's essentially how the picture looks like when you are close to the degeneracy point, to the resonance state of the quantum dot. Then you see something featured around delta, but you see now also feature about 2 delta, and that's because if you will have superconductor to superconductor, the quasi-particle onset would be a 2 delta and minus 2 delta. So that already shows that there is other contact. We have now 2 superconducting contact. There is this line going through, and then there seems to be this kind of an Andreev bound state coming in here, which has anti-crossing with the dot state. That you see this anti-crossing feature very strongly, and there's some feature inside the gap which has to do with the softness of the gap. But I mean, it's a kind of it's an intriguing, nice picture here, and this is going to change when we change the gate voltage. Now my mobile phone says it's 19. I'm just at 90 minutes. Let's see, can I turn this off? Oh my goodness. All right, so when you increase the gate voltage, what you then see is it's all of a sudden you see this an Andreev bound state coming also from the other side, and it starts like anti-cross with the dot state, and again there's a couple of features inside here, but it looks much more symmetric than it looks here. It's quite asymmetric in this picture, and then and the way we can understand this is quite simple. So maybe I just don't show a model. It's just immediate because time is running out. So just try to explain what happens. So what happens in the beginning when you above pinch off, and then what will happen, because this section is short. So there's at some point an onset of superconductivity appearing here. The Andreev bound state forms on the left side. This becomes kind of in the short junction limit, and then you see this Andreev bound state interacting with the dot level. Now, that gives this asymmetric looking feature. Now, if you go further in gate voltage, before this lead was looking like a normal. There were no superconductivity here. But if you go further in gate voltage, all of a sudden this becomes also in the short junction limit. Then you see an Andreev bound state also here. Now, if 2 Andreev bound state, both can interfere or interact with the dot state, and that gives kind of this picture here. Now, if you go then further in gate voltages, you start to see peak appearing here. This is the precursor of superconductivity, increased conductance. If you go very large, you see critical current also in this system. So what happens is essentially we go from a single quantum dot to a dot coupled to an Andreev bound state on the left. Then you have an Andreev bound state also on the right. You could think this is now if they hybridize, it's kind of an Andreev molecule, and then essentially go to a single big Andreev bound state, coupling the two superconductors. Since my time is over, I will not go through this here. I thought this will not work, but just come to the conclusion. So we've been working, we have been measured using built-in quantum dot. They're very nice spectrometers, very stable. Also, they can be tuned. The level width can be tuned between micro EV and 100 or up to even milli EV. We found the soft gap in our system. Don't really exactly know why. We have seen this evolution from Andreev atoms to Andreev molecule, and the last part I couldn't show you. Let me thank you for your attention, and once again, for the organizer to put, must have been a huge amount of work to put this all together. So thank you very much.
Okay, thank you, Christian, for this nice presentation. Unfortunately, we have run out of time, and I think there are questions. Probably I have many, but
I have also an email. I mean, can look at the chat. If the chat is if the questions are in the chat, I can look at it afterwards.
In the chat, I don't have questions now, but maybe in this session, in the special session this afternoon, we can discuss this if we have a little hold, because the session in the morning is too long.
Yeah.
Unfortunately. Thanks a lot, Christian. So let's go now with the next talk, which is going to be from Juan Carlos Estrada, from Delft, who is going to talk about temperature-induced shift of Shushiva-Rusinov resonances. So Juan Carlos, you may start.
Thank you, and thank you for the invitation, for giving me the opportunity to give this talk. My name is Juan Carlos Estrada Saldaña, and I'm a postdoc at QREF at the University of Copenhagen. And today I will talk about our latest results published in Communications Physics, entitled Temperature-Induced Shifts of Shushiva-Rusinov Resonances in Nanowire-Based Hybrid Quantum Dots. Whereas the Condo Effect, which occurs in a quantum dot coupled to a normal metal, has been extensively characterized in biased spectroscopy, gate voltage, magnetic field, and especially in temperature. Shushiva-Rusinov states, which occur when a quantum dot is strongly coupled to a superconductor, are yet to be characterized with as much detail in their temperature dependence. There has been some theoretical works concerning the temperature dependence of Weissar excitations. And what concerns us today is that these theory calculations have predicted that the Weissar states would not shift with temperature. They will remain constant in temperature. This was done in a single impurity Anderson model coupled to a superconducting BCX lead. And there have been some excellent experimental works on the temperature dependence of Weissar states before our work. But these experiments did not focus on the possibility of a shift, probably because the theory came after some of these experiments. And today we will, well, we can say spoiler alert, we will show that actually these Weissar states do shift in temperature. And we will demonstrate this in this setup. We have a quantum dot, which is weakly coupled to a normal metal with a coupling gamma N, and which is strongly coupled to a superconductor with a coupling gamma S. And the strong coupling gives rise to Weissar resonances inside of the superconducting gap. And because the fridge is at a finite temperature, there is also some broadening of the Fermi-Dirac distribution in the normal lead, as well as some broadening of the Weissar resonances in the superconductor. And this setup has been used before by these other groups. So this is how our actual device looks like. We have a nanowire, which is covered by aluminum in 3 of its phases, as seen in these schematics. And the aluminum has been etched on the top part of the nanowire. And then the nanowire has been contacted with 2 titanium gold leads. And this forms a normal metal nanowire aluminum junction. And then by gating, with this local gates underneath the nanowire and these side gates, and as you can see in the scheme, also this packet below the whole device, we can define a quantum dot in the bare nanowire segment here in red. And we are using also these nanowires from Peter Krostrup and from Thomas Karen from Jesper Nygaard's group. And these have this, typically this interface. This is an TM image taken from this paper. And this is a measurement of differential conductance versus source stream voltage. And this shows that the gap is quite hard. And these are the coherence peaks at the energy delta. But as the temperature is increased, this is a temperature dependence measurement, the delta peaks decrease in conductance. They flatten up a little bit. They stay constant in bias. They don't shift. And the gap gets filled by conductance. So the gap gets a little bit soft with temperature. And now let's look at how the actual YSR peaks look. So this is the two YSR resonances inside the gap. This is where the gap is at delta. And well, we saw in this paper that these YSR states in the presence of quasi-particle relaxation, they should acquire a Lorentzian line shape. So we fitted our data to Lorentzians, to the sum of two Lorentzians, because we have two peaks. And what we saw is in the black curve, and this doesn't fit the data. The data is in the red dots. And then we proceeded to fit with the sum of two Gaussians, and to our surprise, the peaks shift fit very well to the sum of two Gaussians. So we're going to use in the following this fit to extract the YSR peak position. We also extract the width and the height, but we won't talk about this today because of time. And this you can see it on our paper, the results concerning the width and the height. So now that we saw how they look at a finite gate voltage, let's see how they look as a function of the plunger gate of the quantum dot, which tunes the addition of electrons into the quantum dot. So then we can see that they make loops as the ground state changes from singlet to doublet in the small loops, and then to singlet in the big loop, and then to doublet in the small loop. And the lines that we're seeing are because of excitations. For example, this is an excitation from singlet ground state to doublet ground state, which crosses zero bias to change the ground state to doublet, from a doublet to singlet excitation. And these are our parameters. We're well inside of the YSR regime where the charging energy is bigger than the gap. So next we corroborate what is the ground state, and we do this by applying a magnetic field, and we semi-split the YSR states. So in the singlet ground state, we have two doublet spin resolved excitations, and we see a splitting here. We see a splitting here as well, and here, and there, and there. On the contrary, loops which have a doublet ground state don't split in magnetic field, and that's how we recognize which ones are doublets and which ones are singlets. Next, we go to the actual novelty of our experiment, which is the temperature dependence. So let's see how this map of differential conductors versus source stream bias and plunger gate voltage evolves in temperature. This we can see in the left animation here. And what we see is as we increase the temperature, the small loops, which are our doublet ground state, they grow and they fade away towards the gap. And the big loops of single ground state, they just fade away, they don't shift. So these loops grow and these don't shift. And we can fit the peak position of this positive bias YSR loop, the right one here. And we find that the peak position fitted with this Gaussian fit versus the plunger gate voltage moves towards the gap. It's akin as pulling the string of a guitar towards the gap. The notes remain fixed in energy. So the first experiment that we did after correcting this is to see if these shifts depend on the coupling to the superconductor. So we're gonna change the coupling of the quantum dot to the superconductor, this coupling gamma S, by changing this gate voltage, which of a gate that is located underneath the superconductor. And we have also that this gate is shorted to this side gate. And we're gonna do this study on the right loop, on this white loop. So what we see is shown here. As we tune gamma S, we're shrinking the loop. So this is the white loop, we're shrinking it. And then it opens up when we go from a doublet to a single ground state. And On the bottom row, we're showing a line cut at the center of the loop. So in each of these loops, we're taking line cuts, and we're plotting this versus temperature. So this is how the YSR peaks evolve in the electron hole symmetric point versus temperature. And we see that they split with temperature. And when we reach the loop that is the smallest, the YSR peaks converge towards zero energy, zero bias with temperature. And when we cross the singlet to the singlet side, they even converge faster towards zero bias, even though they are at the same initial position. So there is a difference between being a doublet, being a singlet, and between the position inside of the peak. So we fit again with the Gaussian to extract the peak position of these YSR states. And this is plotted here, peak position versus temperature. We have in red states which have a doublet ground state, and in blue, those who have a singlet ground state. And we can see two things. The first thing we can see is that the curvature of these curves changes from positive, so shifting towards the gap, to negative, shifting towards zero bias. And we can also see that for pairs of states which have approximately equal initial position, those who have a single ground state shift faster towards zero bias with temperature than those who have a doublet ground state. We can parameterize this behavior by using this G parameter, which equates the position of the YSR peak to this G parameter. And this G parameter is nothing more than the exchange energy up to a constant factor. So we plot this peak position versus exchange energy up to a constant factor. And here we have, in green, we have peaks which shift towards delta, in red, peaks which shift towards zero. And we can see, again, the same thing as here, that before the doublet to singlet ground state transition, the direction of the shifts changes. Next, we studied the coupling of the quantum dot to the normal metal. So we wanted to increase it to see if there is some kind of Condo effect appearing, because we increase the spin, the coupling of the spin to the normal metal, and there should be some screening there happening. And we do this by changing the voltage on this local gate, which is closer to the normal lead. And we do this study on the left loop. And what we find is that as we increase the gate voltage, we go from very faint peaks to very broad and large conducting peaks. And this happens because we're equilibrating the couplings between the left and the right side. And here in the bottom row, I wrote some of the maximum conductance of the peaks. And we go from 0.03 square wave to 1.6 square wave, so fairly conducting. And again, we're going to take line cuts in the middle, and we're going to see the temperature dependence of the peaks. And what we see is that all of them shift with more or less the same rate of 100 microvolts per Kelvin, 100 microvolts per Kelvin. So it seems that the height of the peak doesn't affect too much the shift. They still shift towards the gap. All of them are closer to delta, so they should do like that. We add this additional set, which is measured close to zero bias, again in the same charge state. And this, because it's measured close to zero bias, as we learned from the previous data, it converges towards zero bias with temperature. It doesn't split. And we fit the YSR peaks as we did before, and we plot peak position versus temperature. And we find that peaks that are closer to the gap, they shift towards the gap, and the peak that was closer to zero bias shifts towards zero bias. And again, the same parameterization gives us the same result. We have a change of the direction of the shift with temperature on the doublet side. So just before the doublet to singlet ground state transition, there is a red arrow going downwards. So this is the last slide before the conclusions. And if we want to think about what is the origin of these shifts, I suggest that we should compare the theory model to the actual device. So the theory model is a spin coupled to a BCS superconductor. The actual device, we're studying it in transport. We're studying YSR states in transport. This was a spectral function calculation. And in the transport, we have to add a normal lead. And this lead can lead to a Condo effect. even though we don't observe any zero bias peaks in our data, which could prove that this is the case, this might still be happening. The temperature might just be sparing the Condo effect. We also have an aluminum nanowire superconducting lead. So the lead is not necessarily BCS, it's a hybrid. We have quasi-particle relaxation, even though I don't see how this could change the position of the peaks. And we have a gap that fills with density of states, and we have some broadening because of the normal. So with that, I reach my conclusions. I have shown you that experimental, at least in one device, that usually enough peaks shift in bias voltage with temperature depending on the ground state and their low temperature peak position. And well, the shift is currently not understood. And well, the shift has been seen actually in more than one device. We show data for another device in our publication, which you are invited to consult. I want to acknowledge our collaborators, which are listed here. These people for their fruitful discussions, and these people for the experimental assistance, as well as our sponsors down here. And I want to make a quick publicity. We also work actually with double nanowires, and we are interested in usual states and in the Johnson current in these double nanowires. This is a key image of them. And you can consult the paper, the poster, sorry, of Alexander's Bakeries on Wednesday afternoon to learn more about this. And thank you for your attention.
Thank you very much, Juan Carlos, for this nice and motivating presentation. We are in time, so we can go for some short questions. Questions you may write on the chat, or you may raise your hand. Okay, if there are no questions, so let me say, I want to ask, it's strange that there's no theory for this, for me, Juan Carlos.
Yeah, why is it strange for you that there is no theory?
No, that, I mean, this system has been studied for long, and why temperature dependence had not been, well,
yeah, I find it also strange that there is no theory on this. I think it's a matter of studying transport on the system already calculated by Rock, Shitko, and the other paper. But that probably is hard. It's also a matter of applying temperature on this PRB by Shitko and Aguado and collaborators on this paper by Domansky and Gorsky. I think we have to see what the temperature is doing to that system. And we actually have some idea that, well, in this paper by Domansky and Gorsky, it was said that the Condo temperature should be enhanced on the doublet side.
Yeah.
So before the ground state transition, and this might lead to this change of direction in the doublet side. So with temperature, you know that the Condo singlet will be destabilized. This is schematized here. As the system becomes warmer, the singlet will shift towards higher energy because the Condo phase is becoming weaker in the normal lead. And when we are in the singlet ground state, then basically we will see our behavior. And maybe what we're seeing, the change of curvature, is because the Condo effect in the total system, the normal quantum dot superconductor system, is different than just considering the separately quantum dot normal system.
Yeah, yeah. It was about. I was about to comment this. I mean, you are probably in an intermediate regime, and as you change temperature, you start to increase to have a tricky interplay between Jussi-Barushinov and Condo physics, and it's kind of a tricky regime probably. So this is why there is no theory on that. I mean, because all the theory is essentially numerical renormalization group, which is zero temperature. If you want to put finite temperature, you have to be a bit careful maybe, and I don't know. So I wanted to ask you, maybe you mentioned and I missed it. Do you have like how this temperature dependence changes as you change the coupling to the superconductor? Have you done this kind of measurements? Maybe you mentioned it and I missed it.
This is this measurements right here. So here we're changing the coupling to a superconductor.
Yes.
And this is what we see. And this is that there is a difference when we are approaching the doublet to singlet side. And we extract this from from fit in the peak position. Sorry, I don't understand.
Okay, right there.
Sorry, it was.
So what happens?
What happens where?
To this temperature for different couplings.
So when we are close to the gap, so when we start with a peak position that's close to the gap, we are going towards the gap as we increase the temperature. The peaks shift towards the gap. And as we increase the coupling, we're gonna push the peak position downwards. And then the curvature is changing. It's going from positive to negative. Basically, the peaks are going to be pushed with temperature towards zero.
Yeah, this is the curvature you mentioned.
We can maybe see better. I made a sketch of the phase diagram. Remember this phase diagram, the dome that is just level position versus gamma S over U. If you see the low temperature, you will have a clear border between the doublet side and the singlet side. The singlet side is in blue. This is a color scale, also schematic. But if you increase the temperature, then this border is gonna kind of broaden. Yeah. And that makes all the things go towards zero lines.
Okay, thanks a lot, Juan Carlos. So I think we should move to the next talk, and maybe we discuss this later in the afternoon. And Pasquale Mara from Tokyo University is going to present his work on topologically non-trivial underbound states. Pasquale, when you...
Hi. Can you see my screen?
Yes, yes. Put it in full...
Okay, right.
Presentation mode.
Yes. So, thank you. First of all, thank the organizer for.
We don't see you in the video, Pasquale.
Really? Okay. Here. Okay. Now, I think it's me. Okay. So I want to thank first the organizer for giving me this opportunity of talking about these recent results. This theoretical work which has been done in collaboration with Professor Nita at Keio University. So in this session, we were talking a lot about underbound states, and I want to give another point of view and introduce the concept that there may be also theoretically possible to have some underbound states which are topologically non-trivial. So first of all, of course, all of you are experts of Majorana bound states, but just let me give some highlight, just a general concept. So all the Majorana bound state literature started with this seminal work of Kitaev. So we have this Kitaev chain, which, however, it's a rather unrealistic system because it's spinless and p-wave superconductivity. But then it was realized that one can have a S-wave conventional superconductor with spin orbit coupling and magnetic field and realize the same physics. Also, after that, one realized that one can have no intrinsic spin orbit coupling, but if one has a helical magnetic field, which induces, let's say, effective spin orbit coupling. Then the last step is to consider, let's say, a general dependence of the magnetic field, which can be realized, for example, with nanomagnets or in other systems, where the magnetic field is not only modulated in direction, but also with a non-uniform intensity. So then in all these systems, so we know that Majorana bound states have very clear signatures, like, for example, the zero bias peak, and for example, the localization of the peak, and quantized Majorana conductance. However, as we already seen today and yesterday, these signatures may have another alternative explanation in underbound states. So here, I want, with this talk, I want to give you the idea that one can have also non-trivial underbound states. So let's see how one can achieve this. So the motivation is the fact that basically topological properties of the system does not depend on the spatial dimension of the system. For example, one can have the so-called Taulus pump, which is a one-dimensional system, which lives in a synthetic two-dimensional parameter space, and one can define a two-dimensional topological invariant, which is the Chern number, which describes topological non-trivial states of the system. And this is completely equivalent to the quantum Hall effect from a topological point of view. Then one can have a step further, and one can think about double dimensionality. So basically, for example, one has a one-dimensional topological superconductor living in a one dimension, and one can imagine to have a parameter, so a synthetic dimension, and therefore this system can be considered, can be thought as a system in a two-dimensional synthetic space. And in this case, one may have the coexistence of two non-trivial phases. So one defined by a Majorana number, and the other defined by a Chern number in two dimensions. So usually synthetic dimensions are realized when one has a special modulated field, like a harmonic modulation with a certain frequency, and a phase offset phi. So in this case, the phase offset behaves as a synthetic momentum, so a synthetic dimension. So this system can actually be realized because, for example, one can have a chain of magnetic atoms on a conventional superconductors. So this is one of the realization of a Majorana bound state system. And one can have a modulated, amplitude modulated Zeeman field, because one can have a superposition of a helical spin texture, so the magnetic field induced by the helical spin texture, and one can apply external field coplanar with this helical chain. And in this case, one will have a magnetic field which is periodic in space and also has a non-uniform intensity. So basically, if one can switch off the superconducting pairing and also the spin-orbit coupling, this Hamiltonian basically is equivalent to a Harper-Hofstadter or Hamiltonian, which has been studied in the context of Taulus pump and quantum Hall effect. And so what I want to say here is that one has the so this system is one dimension, so one has a one-dimensional momentum, but has this phi here, which behaves like a synthetic dimension. So basically, this system can be classified in 1D and described by a Z2 topology invariant, that is the Majorana number, but also by a Z Chern number defined in two-dimensional space. So let me just have a quick review of this Hofstadter system. So Hofstadter model is a simple one-dimensional model, a tight binding model where one has a field, in this case a potential, so electric field, which is modulated with this, which is amplitude modulated. This has no symmetry, so lives in two dimensions. So one a real dimension plus the synthetic dimension, so it's classified as in class A, so and has a Chern number as a topology invariant. This Chern number is equal to the charge pump through the system, and it can be calculated as the solution of this Diophantine equation. So this is a very well studied model. So this is not only theoretical, because basically one can realize this system, and it has been realized as a similar system. So if one has iron atoms on a surface of a superconductor, so in this case, one has one can have a amplitude modulated magnetic field, which has been measured in this system. So let me. Can you still hear me, right?
Yes.
Yeah. Okay. Sorry. Here I showed basically the results, the numerical results of this work. So here I plot the global gap of the system, which is the particle Hall gap, the minimum of the particle Hall gap, as a function for a different choice of the phase. So, for example, this is the spectrum of the energy band of the system with a Majorana bound state here. So here on the two axes is the applied magnetic field and the intensity of the helical spin, helical field. So one can have a trivial Majorana number, which are these gray areas with no Majorana bound states. One can have a non-trivial state with a non-trivial Majorana number, and this basically, these two patches correspond to the well-studied system of the case of a uniform field or a purely helical field. And let's say these patches can be seen as a perturbation of these two levels. Then one has this white part here where basically the global gap is 0. That means that the gap closes for a certain value of the phase phi, and one can have different values of the Majorana number. So we call this a mixed phase. So this is basically what it looks like. So this is the topic of a previous work. So when I change the phase phi, I can go from a non-trivial phase to a trivial phase. So one has a Majorana bound states, which are so let's say trivial and non-trivial phase are alternating as a function of the phase phi. So, basically, the most interesting regime of the system is this one in red. So basically, one can have Andreev bound states, so dispersive mid-gap states, which are topologically non-trivial and correspond to what we call a particle Hall Chern number, which is defined as very similar to a spin Chern number. So basically, is the difference of the Chern number defined in the particle and in the whole sector. So so this phase diagram is has a coexistence of these two different topological phases. One is the Majorana bound states phase, and the other is this phase with a non-zero particle Hall Chern number, which has dispersive Andreev bound states. And these are these are topological invariants defined in two spaces with different dimensions. So one is defined in one dimension, and the other is defined in this synthetic two-dimensional space. So I just give you some insight about how you define this particle Chern number. Basically, the system, the Hamiltonian of the system can be written as a block matrix. So if one switches off the adiabatically the superconducting pairing, one has basically two diagonal sectors, which are the particle and Hall sector, and one can calculate the particle Chern number analogously as the spin shear number as the difference of the shear number of these two sectors. So, how one can understand this topological non-trivial phase? So basically, it's usually as one can understand this as a band inversion. So here I plot the partial density of states of the spin up and spin down sector and the particle and the whole sector. So one can see that if one increases the magnetic field, one can have at zero energy, let's say one can have the superposition, let's say the alignment of gaps of where the different sector has a different shear number, and which at least one is a non-trivial. And in this case, the particle shear number, can be non-zero. So this is realized if the magnetic field intensity and the magnetic field modulation is strong enough to to reach this band inversion. So this is a numerical calculation of the energy spectra as a function of the applied magnetic field. So this is the bulk density of states, and this is the local density of states at the left and on the right side of the system. So here I just want to summarize the differences between the well-known Majorana bound states and these non-trivial underbound states. So of course, Majorana bound states have zero energy excitation, but underbound states are just mid-gap, so they are not necessarily at zero energy. So more interestingly, so Majorana, of course, is its own antiparticle, so it's a particle-Hall self-conjugate. Non-trivial underbound states are different because they basically come in pairs, so which are particle-Hall conjugated one of the other. And basically they are fully particle-Hall polarized. That means that if one has a purely particle behavior flavor, and the other has a pure Hall flavor, and also they are spin polarized. So since they are dispersive, so basically the energy of the underbound states is not correlated at the two edges of the system. So this is basically the main experimental difference. So the main physical difference between the two that can help to disentangle these two spectra. However, if the particle-Hall gap is very low, so the dispersion of these underbound states can be very difficult to observe, because the dispersion is basically in this context means that if I change the parameters, for example, if I change the magnetic field, I have a change of this energy of the zero bias or near zero bias peak. And from a topological point of view, the main difference is that the Majorana bound states are correspond to a Majorana number, which is defined in one dimension, and the underbound states correspond to a particle-Hall shear number, which is defined in 2 dimensions. So here now I come to my conclusion. So I show you that if one has a system with a spatially amplitude modulated and periodic field, magnetic field, this field can induce 2 different kind of non-trivial states in the superconductors. The first is the well-known Majorana bound state, and the other is the non-trivial underbound state. So, and these 2 different topological states correspond to, are described by 2 different topological invariants, which are living in 2 different, are defined in 2 different spaces. One in the real spatial dimension, and the other in a synthetic 2-dimensional states. So these so the Majorana and the non-trivial underbound states have different properties physically, and also that can be observed in experiments. but they are similar enough where, that one can, let's say, that can be difficult to disentangle one to the other. Also, I think a very confusing property is the fact that since that non-trivial underbound states may be, so they are topologically protected, they appear only after the closing and the reopening of the particle hole gap. And this is basically very, very similar to what happens with Majorana bound states. So basically, the measuring the local density of states and the bulk density of state at the same time, maybe not, it's not sufficient to disentangle these two different non-trivial states. So I think I finished my presentation, and I thank you for your attention.
Thank you very much, Pasquale, for your nice work and the presentation. So we have time for one or two short questions. Maybe there's one here from Elsa, and she says, nice talk. How could you experimentally check that you have non-trivial underbound states instead of trivial ones?
So I think the usually non-trivial, usually trivial understates are associated with disorder, and in principle, if one changes the magnetic field or other parameters of the system, or for example, if one changes the direction of the magnetic field, one should not expect a dispersion or a change of the energy of these trivial underbound states. Of course, it can be a situation where these trivial underbound states may appear or disappear. Instead, for non-trivial underbound states, one has a clear signature which has a dependence. So one has a dispersion. So, so if one changes the magnetic field, one has a change of the energy, and also they appear only after that you close and you reopen the gap. So I would say a way to disentangle these two is to look at how the spectra, the the local density of states or the density of states changes when one changes the applied magnetic field. Yeah.
Okay, thank you. And are there any more questions? If not, we thank Pasquale, and we go to the next one because we have little time now. So next speaker.
Thank you much.
Could you stop sharing? And now next speaker is Mr. Andreev from the Institute of Physics in Poland, who's going to talk on non-abelian dynamics of Majorana states, I think. Yeah, so please, Mircea, when you wish, can start, please. You should go to presentation mode.
Mircea, you were muted. Now,
in presentation mode. Now, yeah, good. Please.
Okay. Something. Okay. Something doesn't work.
You have problem? All right.
Okay. First of all, I'd like to thank the organizers for giving me the opportunity to present here some of.
Sorry, Mircea, can you turn on the camera if you want?
Sorry. Yeah, sure. Yeah, I don't want to.
Okay, nice. Thank you. Go ahead.
Sure. Yeah, so I would like to talk about some recent work that I've done together with Pascal Simon, mostly with Pascal Simon, and some parts with Olesa Dmitriuk and Martin Wysokiński. So these parts will probably, depending on time, I will talk or not about. So if I need to boil everything down right from the beginning into a summary of my talk, I would like to basically explain how I reached this equation and what it involves for Majorana braiding and Majorana dynamics in general. So while my title says it's rather general and has to do with non-abelian dynamics in the presence of a cavity field, I basically, the motivation behind was Majorana braiding that in the end will kind of discriminate between other objects that are non-topological and the actual Majoranas, and also they'll turn out to be useful for quantum computation. So basically the idea is to move around gamma I and gamma J and end up with non-trivial periphases acting in the degenerate subspace that will allow to implement some quantum gates. So that's kind of the goal of the field. Now, it's non-abelian and topological. However, in the end, it turns out, and this is just one paper, but there are quite a few, once dynamics is ignited, even though it's topologically protected by the gap, however, environments such as bosons will start affecting the braiding dynamics, and not in the nicer way, not in an exponential fashion in the gap or in the time scale over which the braiding is involved, but actually as a power law. So there are a couple of papers, that's just one, that says, okay, dynamics might ignite the environment in ways that are pretty detrimental to the braiding. And this paper and some other papers kind of motivated us to kind of say, well, let's turn the tables, and if the environment kind of affects the braiding in such dramatical way, how about looking at the environment and see if you can use it as a resource instead of as a detrimental object. Now, there are various instances where environments are used as a resource, and that's in particular very common in this cavity QED or cavity quantum dynamics with conventional qubits, I call them. For example, superconducting, NV centers, spin qubits, and so on, that are represented here with blue arrows. And they are inserted in an electromagnetic cavity that escapes at some rate k. And this electromagnetic cavity interacts over some distance, millimeter, centimeter long. And it's a witness of the spectrum of the processes of the entanglement and so on. In the weak coupling limit, one can kind of monitor the dynamics of the spins. In the strong coupling, you can get rest states, entanglement, correlation between spins, two qubit gates, and so on. So there is a lot of beautiful physics happening in kind of control environment in a cavity QED setup. So the question then was, okay, we know that braiding is a highly non-local process. In particular, that's exactly, for example, what we want to do. We want to put the Majoranas here depicted in blue. We want to put them far apart so they don't interact and create non-local qubits. And if we insert them in a cavity, now the cavity, as I said, is a millimeter, centimeter long. So these non-local qubits in the end become local objects on the size of the wavelength of the cavity. And now if we move the position R1 and R2 around, the question is, instead of spectrum and decay, can we kind of envision from the cavity response the geometry and eventually the topology of many-body states that define this Majorana subspace. For example, here on the right we have degenerate levels 1, N1, N2, and so on. So N1 would be defined by N Majoranas or N-1 Majoranas that that are living in the manifold. And the question is, well, spectrally, you cannot see anything, you just have an energy gap. Can you, through dynamics, see the geometry of the states and even, you know, manipulate it if you go in a strong coupling regime? So the goal is find non-abelian Berry phases imprinted to photons, and if possible, make the theory general, not just for Majorana. Now, we saw already like amazing progress on the experimental sides, in particular in 1D nanowires, indium antimonide, indium arsenide. And my motivation was that a while back, I was interested with Daniel in nanowires for quantum computation with spin qubits in these systems. And turns out that the coupling between cavity fields and electron charge as well as electron spin in the system can be rather large. So in principle, these nanowires that are built from Narana are a good platform to use for cavity QED. Now, these nanowires, of course, there are many schemes for kind of using and implementing dynamics. And this is just one scheme used for implementing braiding. Here, I give one reference. Of course, there are many that beautifully explain how braiding works for nanowires. We have a tri-junction, for example. So we have each wire contains two Majoranas that meet at the center and form a big fat gamma zero, which gives rise to some effective Hamiltonian described by these four Majoranas. So the goal now is to exchange, for example, gamma 1 and gamma 2. So basically, I want to go from this kind of dynamics of Majorana in an abstract sense to something that actually can be done in a lab. So I want to give a particular example. So the effective Hamiltonian is the interaction between this big fat Majorana in the center and gamma j at the edges. And of course, there is some theoretical procedure that tell us how to describe such system. So this system, which is 4x4, is decoupled in two blocks for each parity. So if parity is 0 or 1, which means I have one electron or 0, but it's more like the product of gamma 0, gamma 1, gamma 2, gamma 3 that is fixed. So the Hamiltonian is block diagonal, which means that for each 2x2 Hamiltonian, we can depict it as a spin. So we map the entire problem to a spin 1/2. However, each block depends now on tau, as you can see. We have delta 1, delta 2, and delta 3, and the only difference comes to delta 1 there that depends on tau. So the spectrum is degenerate for the two, the only difference being this tau, this parity. And as I said, there is a procedure which I will not go through, how to braid this, and that gives you that, during the procedure, by changing these splittings, either by applying many procedures, by changing the tunneling between the Majoranas, or by changing the fluxes, Coulomb interaction between them. So there are several procedures through which one can exchange gamma 1 and gamma 2. And there is a nice mapping of the entire problem to a block sphere. And I'm trying slowly to approach something that is very well known. So we have this block sphere analogy that tells us, okay, this braiding is analog of this trajectory on this effective block spin for this effective spin, that basically it encounters 1/8 of the northern hemisphere of the block sphere. So we have this spin analogy. And now, having this spin analogy, it's very helpful, as you will see. We add the coupling to the cavity. And the coupling to the cavity, basically what it does, it can do many things, but one of the things, it can change this U1, U2, U3. So the coupling between the Majorana, it shakes them. So it can change either the overlap of the wave function or the fluxes that leads to coupling between them. And in the end, what it only boils down to a very simple Hamiltonian that we call Majorana photon coupling, that looks like just a delta vector plus some small delta that pertains to the coupling, A dagger plus A, and this gamma vector is just the vector formed by gamma 1, gamma 2, gamma 3. So we reduce the problem so that we kind of get something that we know. So for each block of this 4x4 that I mentioned, now we can basically map everything to a spin Rabi model that contains this HM that depends on tau. And again, it's a very simple Hamiltonian. Of course, it's time dependent through this delta tau of t. And again, the spectrum, sorry, the instantaneous spectrum of the two parities is exactly the same. So of course, the cavity field doesn't discriminate through the spectrum to conventional kind of spectroscopy, the two parities or the Berry phase at all. Now, here on the right, I show what's the Berry phase associated with the trajectory on the Bloch sphere, which is pi over 4, so that's how we can calculate it. And starting from this Rabi model here, that is just delta sigma a dagger plus a, one can perform a usual dispersive regime. However, in a time-dependent fashion, assuming at the moment just the adiabatic limit. So basically, the coupling to the cavity and the velocities on this Bloch sphere, so the braiding velocities are much smaller than the detuning between the cavity field and basically the Majorana qubit. And with that in mind, after a bit of algebra, one ends up with an equation of motion for the photonic field that, as it's very well known, it gives rise to, of course, the dynamics is given by the bare photonic field omega 0 plus a renormalization delta omega that contains G0 of t, which is the instantaneous dispersive coupling between the cavity and the spin of the Majoranas, plus a term that depends on the velocities now, which lambda beta tau, where beta tau, it's like as I show on the right, is theta and tau phi. So even though the instantaneous spectrum doesn't know anything about the splitting and about the parity, the dynamics that imprints into the photons through this delta omega knows about the tau through very, theta t and capital phi, which capital phi is again a phase basically captured through some unitary transformation by the coupling between the photon and the Majorana. So it's a bit of algebra, but in the end, it boils down to a very simple expression. So dynamics, it's the sum of this parity-independent plus non-adiabatic contribution imprinted with the geometry of trajectory and the parity of the ground state. So definitely dynamics, even if it's degenerate, it still can find discriminate between these two states through geometry. Now, of course, that was the adiabatic regime, where the velocity of the braiding, or how I do the braiding, it's much smaller than the coupling. And now, what we do a floquet. Sorry. Oh, shit. Sorry. So now, I apologize. So in the case where the dynamics it's slower, it's not slow, we can do a floquet approach still in the dispersive regime, and then find what's the cavity detuning average over a period of the braiding. And what we can find is that this imprints into the denominator of the following expression. So the detuning explicitly contains the Berry phase associated with the braiding and the parity of the ground state. So both of them are there. So now what you can do, you can start to detect, do spectroscopy of the braiding. And what you end up is sending some light electromagnetic waves from the left and collecting them on the right. So doing this input-output detection. So now we open the cavity, we get some escape rate kappa, we get some input field that some coherent state that we insert, and then the transmission of the cavity then will be affected by this delta omega that depends on tau and gamma b. And of course, we also add some capital gamma line width of the levels just to kind of get a better signal. Now you can look in the transmission, but you can also look in reflection to kind of see better. Of course, both are equivalent. And if the Berry phase is 0, there is no difference between the two parities, so the signal will overlap. However, if the Berry phase is pinned at pi/4 and is topological, you will get these two kind of shifted signal in the spectroscopic measure as a function of the precession frequency. So by looking at the precession frequency dependence, you will see a clear dependence between on the parity and on the Berry phase. Then you can also look at as a function of the detuning, delta minus omega 0, and both in the transmission and also in the phase shift of the photons. And clearly there is a spectroscopic evidence, at least in theory, that there is a difference between these two parities, and that difference is pertains to the Berry phase associated with the braiding. Eventually, one can find this braiding phase by looking at the peaks as a function of omega and extract it from a spectroscopic measure. So that would be kind of the application, and that was kind of the initial approach that we've done to look at the specific model and see how we can extract, or if at all, the Majorana couples in the general subspace to the photons. So the question then was, okay, can we make this more general, and can one understand it better from some more general principles? And of course, there are already some works in that direction, which is was very useful. The idea is the following. So this is more like for theory aficionados. Now, if you want, if you have the system that depends on lambda, which lambda could be the position of the Majoranas, and you add the environment, now you distort these energy levels, and assuming that the spectrum is not affected by the environment that you add, but what's affected is only the geometry of the state, so you don't leave the degeneracy, then we distort the levels, and the geometry, initial geometry, and the photons of the environment, they have influenced each other. And without the environment, we know, so if we have n1 level degenerate, n2 level degenerate, n3 level degenerate, and now we change lambda, for example, again, the position of the Majoranas, you just can write a simple Schrodinger equation for the evolution of the states of the system. And for simplicity, you can move in the rotating frame, and you get some evolution that depends on this velocity of lambda, so how fast you move. And eventually you can define the Berry connection and the non-abelian Berry curvature associated with each of these n1, n2, n3 blocks. And eventually you find an evolution operator over, if you're interested in cyclic motions, the fact that you come back to the original motion, that pertains to this non-abelian, or could be even abelian gauge potentials that tell you how you manipulate your wave function in the degenerate ground state. So that's what you are after, also with the Narana braiding or other means. And now I will not dwell too much. I will just kind of show you briefly what we kind of did in a very compacted fashion. So now you can add the environment following basically a nice description by Schnitzko, Egger, and Geffen. You can add the environment by just saying, well, the environment just shifts your positions, lambda t, that can be the position of the Majorana. It adds some delta lambda t, and now you can add and solve perturbatively this delta lambda t, but you have to do it carefully in a time-dependent perturbation theory. And if you do it that in time-dependent perturbation theory, you end up with various terms. So there is a very nice term, linear coupling the Berry curvature of this delta lambda mu, that is the environment, to the velocity through the Berry curvature. And doing this theory, we realized that while they stopped at this order, by this theory, we are able to find exactly what I just presented in the previous part of previous slides, that this quadratic coupling to velocity is exactly this frequency shift that imprints into the photons. And for example, for our case, it turns out that this tensor, O mu gamma, it's a geometrical object that, again, for theory aficionados, is A mu, the Berry connection, times the metric, quantum metric of the system that measures the distance between the quantum states. Even more, we went even further, and we found, again, second order, but taking the velocity of the environment itself, because the environment can be dynamic, that we can recover some previous results, also by Pablo San Jose, Zarand, Schneermann, Schoen, and ourselves, where we're dealing with the geometrical dephasing of spin qubits in quantum dot. So somehow the theory kind of takes into account everything. Now, if these delta lambda are quantum, you can basically write delta lambda mu. It's some delta mu A dagger plus A. I didn't write it here, maybe I should have. And you can write the equation of motion based on these three terms that I show above that accounts for the Baire equation, the Baire velocity, omega 0, the instantaneous splitting of the that is obtained in static cases, and the velocity terms that affect both the frequency shift and, in principle, can also pump photons in the cavity. So that's kind of the take-home message that I would like to share. And now, of course, one can look at some outlook, other controlled environments, entanglement, braiding, and so on. And finally, this is a short summary of my talk. We look at dynamics of Majorana bound states in a cavity. We saw how it influences what's the Berry phase transfer into the photons and the signature of input-output detection. And we also try to generalize a bit and see where all these results are coming from. Okay,
thank you, Mircea. I'm sorry for having to cut the questions because we are now more than 10 minutes in delay, and unfortunately, well, I think there is a question, but Yuval, if you don't mind, we leave this for this session in the afternoon, special session where we can discuss. We can have some discussion on all the talks. Okay, so let's go with the next speaker, who Sungun Park from Universidad Autónoma of Madrid, and he's going to talk about circuit QED beyond the James Cumming models. So Sungun, whenever you want, you can share your screen.
Yes, can you hear me?
Sure. Yeah. Perfect. Yeah, you can start.
Okay. Thank you very much, Alfredo. Here, I'd like to talk about the theoretical work on the readout of quantum circuits, which is published last month. So this work has been done with the great collaborators, the Alfredo in Madrid and the Quantronics group at Sapley, and Leandro, who was in the Quantronics group, but then now moved to the Bariloche. Here the circuit QED experiments that basically they consist of the microwave resonator coupled to the quantum circuit. This quantum circuit can be either fermionic or bosonic system having some discrete levels there. So here we send the microwave signal and prove the reflected signal through this microwave resonator, from which we read out the stage of the quantum circuit by measuring the shift of the resonator frequency. The example of the fermionic system is the atomic contact, and for the bosonic system, there are flux qubit and the Cooper box, and the systems have some discrete labels shown in this the middle panels, and these labels depends on some experimentally controllable parameters, namely the superconducting phase difference delta, and the flux phi e, or the reduced gate voltage Ng. So now I'd like to start with the brief physical backgrounds of the work by considering the simplest model, which is the microwave resonator coupled to the two-level quantum circuit system with the coupling strength G. For the case that the detuning parameter D is much larger than the coupling constant G, and for the strong coupling case, there are the two interesting limits. One is the dispersive limit, where the detuning parameter is not very large, such that the exchange of the virtual photon between the resonator and the quantum circuit is allowed. The other limit, which we call adiabatic limit, is that the detuning parameter D is very large, so that the virtual photon exchange process is strongly suppressed. In the limit of the dispersive, it is known that the system is well described by the James Cumming model with the states-dependent frequency shift delta omega R. In the opposite limit of the adiabatic limit, it is known that the band curvature give rise to the effective capacitance or the inductance, which would result in the shift of the resonator frequency. The issue that I'd like to point out here is that the connection or the relation of the resonator frequency shift in the two limits has not been established. So the main message of this talk is that we found the unified theory in which the resonator frequency shift can be understood in the two limits in a single expression. The physical importance or the benefit of this formula is that it allows us to analyze the experimental data in the large range of the transition frequency. So let me give you details on how we get this expression. So this is the model that I considered. Here we have a resonator coupled to the quantum circuit, and the HQC is the Hamiltonian for this quantum circuit. Here X0 can be flux or the charge, and the Hamiltonian has the eigenvalue EI and the eigenfunction phi I, where the I means the discrete level index. Due to the 0 point fluctuation of the resonator, we have some small fluctuation denoted by X all had in this quantum circuit. This XR is proportional to the sum of A dagger plus A when the resonator and the quantum circuit coupled inductively, and the XR is proportional to the A dagger minus A when the two systems coupled capacitively. Here, the lambda is the coupling constant. Now we expanded this HQC up to second order in very small quantity, this XR, we get the this coupling Hamiltonian HC. Now using the perturbation theory for this, the full Hamiltonian HR plus HQC plus HC, we get the correction to the energy eigenvalues of the second order in this coupling constant. Now we can further evaluate the corrections by looking at the relation between this H prime and H double prime. Here the H prime and H double prime denotes the first and the second derivatives with respect to this x0. Here we have from the Hellman-Feynman theorem, we have equation 1, and we have equation 3 from the quantum circuit equation. By doing derivatives on both sides of these equations 1 and 3, we get the equation 2 and 4. By substituting equation 4 to equation 2, we get the relation between this H prime and H double prime. Here, the H double prime is now the sum of the curvature and the matrix elements of the H prime. If we substitute this relation into the perturbative result, we arrive to this form of the resonator frequency shift, which is now in terms of the curvature omega prime prime and the matrix elements of the H prime. Here the Now the expression in the adiabatic limit can be simplified because the 3 terms in the parentheses becomes 0 in the adiabatic limit, where the resonator frequency is very small compared to the transition energy. So in this case, now the curvature effect determines the full shift of the resonator frequency. On the other hand, in the dispersive limit, where the resonator frequency is the comparable or not so different from this the transition energy, the resonator frequency dependent term becomes important, and the expression can reproduce the shift derived from multi-level James Coming models studied previously in this reference. As an example to see how this formula works, let me consider the short weak link. Here the circuit illustrated in magenta is the resonator, which inductively coupled to the superconducting loop containing the Shuttlewick link, which is described by the transmission amplitude, transmission tau, and the phase difference delta. Here, in the middle, you see the Andreev levels for transmission point A. For simplicity, I consider only the two levels, the ground stage 0 and excited 1. The upper rightmost panel shows the transition energy as a function of the phase difference delta. Here, we choose the 3 different values of the resonator frequency, the 1.2, 0.7, 0.1, which belongs to the regions of the dispersive, intermediate, and the adiabatic respectively. So the lower 3 panels corresponds to the frequency shift for each the values of the resonator frequency. Here in the dispersive limit, I'm sorry, here the colors, all plots in red denotes the total shift of the frequency, total shift of the resonator frequency, and the green and the blue denotes respectively the curvature contribution and the James Cumming contributions, as shown in this the full expression below. So in this dispersive limit, the James Cumming contribution is very close to the exact shift around the phase pi, and very well describe the anti-crossing behavior. In the adiabatic limit, the curvature contribution gives the exact result, which is the total shift of the frequency. And there's some deviation from this James Cumming contribution. In the intermediate region, there's some the main contribution smoothly changed the James Cumming contribution around the phase pi to the curvature contribution around phase 0. As a second example, I consider this the Cooper pair box, where the corresponding circuit is illustrated in black in this circuit diagram. Here, HCPB is the Hamiltonian for this the Cooper pair box, where this EC is the charging energy and the EJ is the Josephson energy. Here, NG is the reduced gate voltage. By solving this the Hamiltonian, we get the Andreev levels shown in the lower panels for the different values of EJ over EC. As you see clearly here, the band structure depends on this quantity EJ over EC. So probably we expect that the frequency shift also would depends on this quantity EJ over EC. So now we calculate the frequency shift for this lowest and levels at the NG equal 1/2 to see this dependence of EJ over EC. Here, this is the shift as a function of the resonator frequency, Here, x-axis is the resonator frequency divided by the transition energy, and the blue and the green lines that corresponds to the James Cumming contribution and the Coverture contribution with respect to the total frequency shift. Here, for very large, the value of EJ over EC, you see the James Cumming contribution, and this the Coverture contribution only gives the exact result at the 0 and 1, and if we increase this value of EJ over EC, this James Cumming contribution approach to the total frequency shift over the large range of the frequency resonator frequency shift. Now, by considering the two-band model Hamiltonian, which is constructed by considering the two charge stage 1 and 0, we are able to get some analytical expression for this the frequency shift around the 0 and 1. So from this the analytical expression, we can see how these curves depends on the EJ over EC. So here, for example, around 1, we see that the slope of this James Cumming contribution is linear in this the EJ over EC. So now I'd like to summarize here with the presented theory which bridges the dispersive and the adiabatic limit, and this theory is applicable to the post-bosonic and the fermionic systems with the multi-levels. And the benefit is that the formulation provides the ways to describe the circuit QED experiment over the large range of the transition frequency. This benefit will be presented in more detail by the next speaker, Cyril, with very nice experimental data. Thank you very much.
Sungo. Thank you, Sungo. So let's see. I think we are short of time, and there are no questions in the chat. So perhaps we should go to the next presentation which is complementary to this one. So okay. The next speaker.
So I stop the sharing.
Yeah, thank you, Sung. Thank you, Sung.
Thank you very much.
So next speaker is Cyril Metzger from Saclay Quantronic Group, and he's going to talk about circuit QED with phase bias, just on junctions, or just on wigglings. Have to stop sharing. Oh, okay.
Good morning, everybody. Can you see my slides?
Yeah, but you should go to full screen presentation mode. Yeah, but this
okay.
This is the previous talk.
Yeah, no, it's okay. So, so yeah, it was just to make a connection. So
sorry.
In the previous talk, Sumun presented us a theory that was able to bridge the dispersive and adiabatic regimes of the read of a quantum circuit. And for this second part of our talk, I'd like to specialize, to elaborate a bit on the case where the quantum circuit of interest is a phase-biased Josephson weakling. Now, within these few minutes, I will try to show you how this theory that Suman presented is able to explain recent experimental data that we obtained both on superconducting atomic contacts and semiconducting nanowire junctions. So the system I'm considering is a phase-biased Josephson weakling hosting some Andreev bound states, which is embedded in a superconducting loop threaded by a magnetic flux phi, which is used to phase-bias the junction. And the loop is coupled to a LC microwave resonator, which is used for readout. Now, using microwaves, it is possible to drive transitions between the Andreev bound states that live in the weakling. And this can be done either by means of the electrical field of a microwave drive sent through a lateral gate, or by driving current in a flux loop coupled to the superconducting loop. And I will discuss these two possible ways of driving the system at the end of my talk. Now, Josephson phase-biased weaklings are actually an interesting exception in the family of superconducting circuits, because the excitations are not collective modes of the circuit, but they are fermionic excitations by nature. And so they give rise to an atomic-like spectrum of energy levels. In the zero length limit, one conduction channel gives rise to two spin-degenerate Andreev bound states. And so the lower one is populated in the ground state, and then in the excited state of even parity, you just create two quasi-particles in the opposite. And so by increasing the length of the junction, more and more states appear in the gap. And so a new family of transition emerges, depicted here in green. So the so-called single quasi-particle transitions, which are atomic-like transition from one Andreev level to another. So for nanowire weaklings, there is an extra ingredient, which is the spin-orbit coupling, and it's responsible for lifting the spin degeneracy and giving rise to spin-split Andreev levels. And so in this case, one really has to deal with the full multi-level nature of the Andreev spectrum and the spin character of the levels. What's important here is that the resonator frequency is shifted because of the coupling with the Andreev levels, and this shift depends precisely on the microscopic occupancy of the Andreev states. So by sending microwaves, we drive transitions between these states, and so we change the resonator frequency shift. And this is what's used in microwave spectroscopy. This has been used in various systems to probe the Andreev spectrum. So, for example, in one atom contact between superconducting electrodes, it has been possible to study the short junction physics and to probe the coherence of the so-called Andreev qubit. And more recently, in indium arsenide weakling, we have been able to observe these single quasi-particle transitions that I was mentioning, and that are a signature of the spin-split nature of the underlying Andreev levels. So in both cases, using the circuit QED toolbox, we have been able to probe the Andreev spectrum. However, with indium arsenide weaklings, the signal that we measured has puzzled us for some time because it's quite different from the dispersive-like type of measurement that one usually performs and that we were used to when dealing with atomic contacts. So in this two-tone spectrum, for example, we had pair transition anti-crossing with the resonator at 10 gigahertz. And so what's plotted here in color scale is the amplitude of one quadrature of the field, of the measurement field after homodyne detection, and is directly related to the resonator shift. And you can see that as one goes, as the transition crosses the resonator, we go from red to blue, so from positive resonator shift to negative, which is exactly what we expect in dispersive measurements. However, for INS data, you see that we also measured similar features of change of sign along the line intensity. However, in this case, the transitions were very far from the resonator, which was at 3 gigahertz only. And so this really convinced us that we were in need of a more general theory that would go beyond the dispersive regime to be able to explain such data. This is what motivated this work that I'm quickly reviewing today. So the main message of our work is encoded in this equation that Sumun already presented, and it gives you the frequency shift of the resonator associated to a given Andreev bound state I sigma. So for example, if the level 1 down here is occupied, it would contribute to shifting the resonator first by its intrinsic curvature, so the second derivative of the level's energy with respect to the phase, and also because of all possible virtual transitions between these states, 1 down and the other, so 2 down, 2 up, etc. So these virtual transitions involve emission and absorption of photons with the resonator. So I'd like to stress here that despite the apparent simplicity of the equation, it can be actually quite tricky to implement it in practice when we have to deal with the multi-level nature of the Andreev spectrum in finite length junction. Not to mention that in finite length junction, the matrix elements as well, the GIJs, do not assume an analytical form. So how would you do in practice? What's the recipe for computing the resonator shift? You would first start by computing the shift in the ground state G. And this illustrates the specificity of fermionic systems compared to bosonic ones, because you really have to sum over all populated levels of negative energies. And then you can compute the shift of many body states, because you can construct it from the ground state by adding either electron-like excitations or hole-like excitations. So to compute the shift in any many-body state, you would just add to the shift from the ground state the contributions from all the levels that you populated above the ground state, and subtract all the partial contributions from the levels where you removed the quasi-particle. So let's illustrate this the simple case of a one-channel zero-length junction. So in this case, everything is very simple because we have analytical expressions. So both for the energy of the 200 bound states, for the matrix element of the current operator that is coupling them, and so we also have analytical expression for the shift. Now, because we have only 200 bound states, there are only 3 states that you can build. So the ground state that I already presented you, and then the odd parity state where you would add 1 quasi-particle, and the excited state which correspond to 2 excitations. So I'm not gonna, in the interest of time, I'm not gonna give you the details of the computation of the shift, but just show you the theory on 2 illustrated cases. First, when the transition from ground to excited state is strongly detuned from the resonator, and in the second case where it crosses it. So in the first case, because the qubit and the resonator are not on speaking terms, the exchange of photons is strong with the resonator is strongly suppressed, and so the contribution to the shift from virtual transitions here in blue is almost 0. And so the total shift experienced by the resonator in red is almost entirely given by the curvature of the ground state. Now in the second case, you see that this time the resonator shift in red, the curvature is not enough to capture the shift, and that this time the contribution from the virtual transitions between Andreev bound state is significant, and in this case you can really capture the shift only by James-Cummings-like description. However, far from phase pi, James-Cummings would fail at describing the shift, which is still given by curvature. Now, in the excited state, the shift is almost opposite to the one in the ground state, and so you can, I plotted here the difference in excited and ground state, which is what we actually probe in two-tone spectroscopy. And in the odd state, the shift is almost 0, but it is remarkable that although this state does not disperse with flux, carries 0 supercurrent, it still contributes to a finite resonator shift, due to contribution from the continuum. Now let's see how we can apply this to understand data that was obtained with atomic contacts with a single channel. So the atomic contact was embedded in a loop that was coupled to a lambda 4 resonator measured in reflection. And I'm showing you here on this left plot the magnitude of the reflection coefficient as a function of the phase difference and the frequency of the measurement tone. And in this case, we had an Andreev transition anti-crossing the resonator. And for each phase flux value, we extracted the position of the frequency, and we could fit this very well with the theory. And in this case, generalized James Cummings description was enough. And you can see that in a significant part of the time, the system also resides in the odd state. And in this case, the resonator is not shifted, and you can access its bare resonance frequency. Now here is the two-tone spectroscopy of the associated Andreev transition here, which was anti-crossing the resonator at 10 gigahertz. And I'm overlaying on the right the theory which we were able to produce. And you can see how well we were able to reproduce the spectrum, both the change of sign as the transition crosses the resonator and also the fine details of the spectrum. Now, I'd just like to flash another result, which was obtained in a slightly more complex situations because we had to deal with multiple channels this time. So in the spectrum, we had 3 Andreev transitions, and 2 of them were anti-crossing the resonator. And this time again, here is the theory, and we were able to get really good agreement and reproduce most of the features in the two-tone spectrum and understand the line intensity. We were also able to fit the resonator frequency shift and understand the small details of this spectrum that was obtained with vectorial network analyzer. Now let's move to indium arsenide nanowire junctions. So in this case, we were measuring single particle transitions that were very far from the resonator frequency at 3 gigahertz. And in this case, the frequency shift was mainly given by the curvature. So here, positive curvature contributes to negative energy shift and the opposite around phase pi. Now, it was quite interesting for us to see that in a different group at Yale, using a different setup, they were also able to measure single quasi-particle transitions. But in this case, only the outer 2 transitions, the one corresponding to spin-conserving transitions, were visible. And they could only evidence the inner transitions, the one corresponding to spin-split processes, at the cost of driving strongly with a strong power. In this case, they were driving the system through the resonator, and which is different to us, where we drive through the gate. And this told us that there seemed to be some spin selection rules at stake here. So we realized that actually in this system where if you drive only through flux in a model, in a fully ballistic model where the transverse spatial symmetry of the nanowire is preserved, the current operator does not mix transverse channels and only spin conserving transitions are allowed. So you would only be able to excite these transitions from 1 up to 2 up or 1 down to 2 down. However, if you drive the system through gate, then the AC signal that you send induces a perturbation in the electrostatic potential that fills the nanowire. And this breaks the rotational symmetry and couples the states on different subbands. So in this case, spin flip transitions would be allowed. So you would be able to excite 1 down to 2 up and also 1 up to 2 down. But let me stress here that this only works if the induced potential has some anti-symmetry in the section of the nanowire. So to finish, let me show you a more recent spectrum that we measured, where we also evidence some single quasi-particle transition. And on this quadrature, you can see that we indeed, using a gate drive, see with similar intensity the 4 transitions. However, in the other quadrature of the field, you see that the line intensity has many changes of sign. You go many times from white to black. And so in this case, it's very different from the simple case, from the simple nanowire spectrum that I presented before, where the shift was mainly due to the curvature. Here, the situation is very likely to be much more complex because the transitions, as you can see, are very close to the resonator. So this times both the curvature and all the virtual transitions between Andreev levels contribute. And so for some given values of the flux, it is possible that the energy of virtual transitions match the frequency of the resonator, and this is what gives all this change of colors here. So you can see here intermanifold spin conserving transitions in blue, which correspond to this process here, and also the inner lines, which correspond to spin flip transitions. And it also came to us as a big surprise that we actually were able to see also another kind of transition here that correspond to spin flip transitions within a manifold. So this was only possible to observe because we were driving through gate. And I think the next talk by Yale will deal more specifically about this kind of transition and the possibility of making an Andreev spin qubit. With this, I'd like to conclude. So we've presented with soon a theory that was able to describe the coupling of a resonator to a multi-level system of Andreev bound states. And we have applied this theory on experimental data. In the case of atomic contacts, everything is analytical and quantitative agreement is reached. And for indium arsenide nanowires, in the general case, it's less straightforward. But still, with this theory, we were able to understand and capture some features of our spectrum, like the effect of curvature. And I also discussed about the effect of driving the system either through gate or through flux and the existence of spin selection rules. Now, thank you for your attention. And I'd like to finish by thanking all the people that were involved in this project. So Sumun and Alfredo from Madrid, and also our colleagues, theoreticians Leandro Tossi and Andrés Reynoso from Baicero, and my colleagues from the Quantum Group. Thank you very much.
Thank you, Cyril. So we have time for maybe one or two short questions. You may either use a chat or raise your hand.
No question?
I don't see it.
In this case, maybe I can tell you a bit more about this spectrum, which was quite interesting. So you see that actually Andreev transitions were splitted. And this is actually an effect from the inductance of the loop. So because of the screening currents in the loop, the phase drop across the junction is not simply given by the reduced flux, but you have to take into account the current that is circulating. And so for a given value of the flux, the phase across the junction depends on the current circulating and so on the exact frequency of the Andreev bound states. So here we had 3 channels. And so, for example, on this line associated to the second channel, so we do the transition from ground to excited. But then we can assume that the 2 other channels can be both in ground and the out states. So we can have 4 different occupancies, and so this gives rise to 4 different lines. So we first looked at this as an imperfection from the way we were phase biasing the weakling, but it turned out that we could reproduce this very well and extend the spectra using the theory that was developed. So, this also tells you that, shows you how you can really probe the microscopic occupations of the channels, which you have a signature in this spectrum.
Okay. Thank you, Cyril. So
Thank you very much.
we should come with the next speaker. So that I tell you that there is a change in the order that because the two next talks are from Yale, from Bala Fatemi and Max Hyde, and this is going, well, we're going to change the order in the original program. So the next first talk is going to be by Bala.
Apparently Bala is not around yet. Maybe he got asleep or something. So Max is here, so he will start.
Okay, you start, Max.
Max is here, but Bala is not around. So let's start with Max.
Okay,
and what happened?
Too early for you. Sorry.
It's too early. Maybe he got asleep or something.
It might be.
Okay, go ahead.
Please, Max. Thank you. So he's going to talk about the realization of Andreev spin qubit.
Look good? See my slides?
Yes, yes.
Thank you, Alfredo. Yeah, so today I will be talking about Bala and I's work, realizing an Andreev spin qubit. So our system is very similar to what was talked about in the last talk. So yeah, we're looking at Andreev bound states. We have a weak link composed of two superconductors, and then a normal region in the middle. So single Andreev bound states. There's been a lot of interesting work done on superconducting point contacts in the Singlet group. We saw a little bit of data on that in the last talk. In nanowire-based weak links, it's been shown that you can make gate-tunable qubits, and then we also saw in the last talk that we can look at new spin orbit physics, also in indium arsenide nanowire weak links. So what we think, one of the reasons we think Andreev bound states are so interesting is that they actually give rise to the current operator of the weak link. And this means that you can couple to them and probe them in ways that aren't possible with states in a electrostatically confined quantum dot, for instance. So here I'm showing the weak link embedded in this flux loop. And this current J can flow around the loop. So even though we have these localized spin states, we have this macroscopic supercurrent that we can couple to. And then we can imagine putting a capacitor in parallel with this inductor, and then we have a resonator, and then we can probe the system using circuit QED. And as we saw again in the last talk, this is an extremely powerful platform. So we have these localized spin states. They give rise to macroscopic supercurrent, lets us couple in via QED, and this can let us do measurement and manipulation of these spin states in new ways. So yeah, we want to make a qubit out of these spin states in particular. So let's start with Andreev bound states in the short junction regime. So an example of this, what are these atomic point contacts? We have an SNS junction again, but in this case, with no length effects, these spin states are degenerate. We just have these two Andreev levels sitting at some area in the gap that can be brought down to quite low energy using flux, but they are spin degenerate. If a quasi-particle falls in, it in principle does have a spin, but we can't detect it or manipulate it. So instead, what we do is we take advantage of the long junction and spin orbit effects. This does a couple things. It brings us to this regime where we can have multiple doublets. And thanks to spin orbit effects, in combination with the flux, this actually breaks the spin degeneracy. And so we can have two doublets. So we still have this lower doublet, these two spin states, and we're going to label these as spin up, spin down sub Q for qubit. These are going to form our qubit states. And then we also have this upper doublet, spin up, sub down sub A for ancillary. And these states, while they don't form the qubit, are going to be critical both for readout and manipulation of our qubit. Yeah. So So we have our cubic states and our ancillary spin states. So there are two things we need to make a qubit. We need to be able to measure it, and we need to be able to manipulate it. So we had this first work looking at the measurement of the two spin states. And now we've turned our attention to manipulation of these spin states. So first I'll go over the measurement side of things, and then I'll progress to manipulation. So just a quick overview of circuit QED. We have our nanowire junction, which I'm representing with this blue symbol here. And then we also have a resonator, which we're going to measure in reflection. So the idea is that we can probe the resonator frequency using this readout tone at omega sub RO. And then based on the frequency of the resonator, that will tell us about the state of the system. So let's walk through that. If we couple these systems via the current operator, as I was talking about before, then what will actually happen is we're going to have a spin-dependent dispersive shift, basically because the transitions of this spin to the upper doublet have different frequency, and they, on principle, also have different G factors. So we'll end up with these two dispersive shifts, chi sub down arrow and chi sub up arrow. If we park our resonator frequency at a particular value, so let's say we park it right at 0, then we'll have these two different chi's. And if we look at this if we look at the real and imaginary parts of the reflection coefficient instead of just the argument, then we expect to see something like this. And so we have the ground state, which is actually where there are no quasi-particles populating the system. And then if a quasi-particle falls into the junction, then we can have these two spin states. And so here's what the data looks like in reality. So we have the two spin states as well as the ground state. So we're seeing that these dispersive shifts of the spin states to the upper level are giving us the spin readout that we desire. And then we can also check what these transitions are doing kind of by actually applying a tone to move the quasi-particle, for instance, from the upstate of the qubit to the upstate of the ancillary doublet. And then we see this second blob pop up, which we can actually see a bit also in the first plot. So now the question is, we can drive these transitions between the doublets, and we can detect the spin state. The question is, can we drive spin transitions with an electric field along the nanowire? So as was talked about a bit in the last talk, we've seen that we can drive spin, these direct transitions that conserve spin between the doublets. But with the flux drive, as we're doing here across the nanowire, it's not necessarily a given that we can also drive spin flipping transitions. But in certain situations, we have been able to observe the inner doublet spin flip transitions. So we can observe the outer transitions in this plot and flux, those are the spin conserving transitions between the doublets. But then these inner lines, those would be what we call the spin flipping between the doublets. So this data was actually flashed in the last talk as well. So this is spectroscopy at pretty high power, and we can see the spin conserving transitions fairly easily. But then in the middle, these dimmer lines, those are the spin flipping ones. So they are much more difficult to see at this particular bias point. But what we found by exploring other gate bias points is that there do exist points where the inner lines are quite bright. And in fact, in this particular case, this is kind of a one-off. The inner lines are brighter than the outer ones. But in general, we can find spots where all four lines are reasonably bright, both spin conserving and spin flipping. And so the question is then, how can we explain the flip of the pseudospin with a longitudinal drive? And the answer was hinted at in the last talk as well, but the thing we've realized is that the selection rule that is, in some cases, sort of only letting us drive these spin conserving transitions between the doublets has to do with the mirror symmetry. So either we can have these mirror symmetric states. So there are various subbands in the nanowire. So for instance, here I'm depicting the lowest and second subbands, which are in space, symmetric or anti-symmetric in the y direction. And we also have the spin states. And so one spin direction pointing in the y direction will be symmetric and one will be anti-symmetric. And so together, these two are going to form our symmetric states of the spin and subband character. And we also have these anti-symmetric states, which we just get by taking the opposite combinations. And so if we have this mirror symmetry, if this mirror symmetry operator here is preserved, then we're not going to be able to drive the spin flipping transitions between the doublets. But in our system, oh yeah, and sorry, and this can also in principle be mixed by this Rochblatt term, the second transverse Rochblatt term. So here, the sigma y dx, this is the term that was giving us one of the spin orbit effects we need in our system, and then there's this this transverse Rochblatt term as well that is going to mix between these various subbands and spin states. In our system, though, this mirror symmetry is not necessarily given at all. In fact, just by the design of the device, we don't expect this mirror symmetry to exist. The aluminum is going to be only on two facets of the nanowire, so this is automatically breaking the mirror symmetry that we had before. Then we also have a side gate. So in principle, this is all going to be mixed up, and this allows us to drive transitions with spin flipping and spin conserving between the two doublets. So there's a bunch of ingredients we need here to get this, but in the end, this is the main point, that this is all mixed up and we should be able to drive the spin flipping transitions between the doublets. However, the direct spin flip transition will still be suppressed compared to these other ones, basically due to perturbation theory arguments. So that brings me to the conclusions of this first part of the talk. And I've shown you that we can detect the spin states of a single quasi-particle trapped in the lowest doublet using circuit QED techniques in both, and also that we have seen spots where we can drive spin flipping transitions and spin conserving transitions at the same time. And this gave us the idea to realize a lambda system. So the idea is that we use one of the auxiliary levels, and then we can drive, we put two tones on at once, drive through a virtual level that's slightly detuned from, say, the up ancillary state. And this should let us do current manipulation of a single spin trapped in the lowest doublet. Thank you.
Thank you, Max. So in principle, so I don't know if Bala would come to complete this second part, or
yeah, no sign. He's not around actually, so let me check again, but I think he's not around. Okay, so just give the second talk.
Yeah, you can give the second talk, or we can go for questions now.
Oh yeah, sure. Let's stop here and yeah.
We can ask for questions for this part. So again, you may use the chat. You may use raise your hand. I don't know what happens today.
There is a question from Charlie.
Oh, Charlie. Okay. What was the difference between the two set points in order to see the inner transitions?
It's just gate voltage bias. So yeah, so Charlie's asking about these two plots, for instance. And yeah, it's just gate voltage bias. As far as we can tell, there's no systematic pattern on whether we can see the inner lines or not with gate voltage. Yeah, we would expect the gate voltage to alter the extent to which the mirror symmetry is broken. It is a side gate, but we don't see a pattern.
Yeah, I think Bala probably was going to talk about this, no, a bit more.
No, not really. I mean, I think that's all the information we have. from the experimental point of view, it's just gate voltage bias. Yeah, I don't think we have a and that a mirror symmetry must be broken. I don't think it.
Yeah, no, just maybe I comment that the breaking of the spin, the conservation is also more likely if you are closer to higher subband. I mean, that's why maybe when you change the gate voltage, you come closer to higher subband. And then
you basically need this entanglement between between spin and So what Alfredo is talking about is that basically these yellow arrows don't show up if you're not close enough to a second subband of the nanowire to the asymmetric band. So you might expect that at higher gate voltages, this entanglement is stronger, and therefore the mirror symmetry can break things more easily, can break the selection rule. This is actually also a given, though, that we need this entanglement to get the velocity asymmetry in the first place that lets us split the spins.
Other questions? Young's research, Elsa says, encourage the young researchers to ask questions. There is a question from Songun Park. If we consider a full shell nanowire, do you expect the suppression of spin flip transitions?
Yeah, I mean, that would certainly make the system more mirror symmetric. So, and if we have a full shell nanowire, then the aluminum would coat all 6 facets. So yeah, the aluminum would no longer be providing a broken mirror symmetry in that case. So,
there is a question also from Cyril.
I don't have it on hand, but yeah, it is in. It is available. It's in our Nature Physics paper. Yeah, we're happy to share it. I don't have it on hand though.
So, you're saying you're answering already to Cyril.
Yeah, sorry. Yeah, the question was, can you show a spectrum on a broader frequency range?
Okay, more questions? Because if we don't have Bala, this is last talk. Unless you Max would like to show anything more.
No, that's fine. I'll move on. Let's see.
So Bala did not show up.
No.
Yeah.
I think it's. But what time is there?
It's 7 o'clock now. It's not too bad.
It's not that bad. 7 o'clock is not that bad.
For me, it would be terrible. Oh, there is something here. No, this is yours. Okay, so then, well, we should close the session now. What do you think, Ramon?
Or well, maybe you can give the talk. I mean,
I'm happy to do either. I can be quick if you want.
Okay.
Yes, sure. I was asking that. Yeah, please.
I'm done being bald. I'm done being bald.
Yeah, just go ahead. If you can, just go ahead.
Yeah, okay. Let's try to summarize it if you can.
Sure. Okay. All right. So second part. So I talked about how we can detect the spin in the last talk. So this is showing the full IQ histogram for the resonator reflection coefficient again. And we can detect these 2 spin states in the ground state. So throughout this portion, I'm going to be presenting data in terms of the probability of finding the quasi-particle in a particular spin state. And we determine these just by these thresholds shown in this plot, these dashed black lines. So our goal is to achieve spin manipulation by using the Andreev levels as a lambda system. So we're going to use the 2 spin states of the lower doublet, and then now I'm going to label one of the states, the upper doublet A, for ancillary. So we have this lambda system, and the first step in driving Raman transitions is actually just locating these two individual frequencies. So to do that, we performed a two-tone spectroscopy experiment. So now the y-axis is probability of finding the system in the two spin states, and then the x-axis is the drive frequency of the saturation pulse that we're going to be applying before our readout pulse. So there are two features. There's a dip around 13 and a dip around 13.7. So the dip at 13, it corresponds to driving a quasi-particle out of the spin up state of the lower doublet and into the ancillary state. So that's why it's a dip. And then same thing with the dip around 13.7. It's driving a quasi-particle out of the spin up state. So we now have found the two transitions that kind of define our lambda system. But yeah, and then we can imagine applying two drives at once, detuning both of these drives. I'm going to be showing blue detuned data. So we're going to be sweeping the frequencies up, F down and F up around in these upper regions. Yeah, I'm going to be using this kind of striped Gaussian thing to represent simultaneous pulses. But there's actually another problem we have to solve before we can move on to Raman transitions. And that's that if you look at the background in this plot, you can see that when we're not driving any transitions, the two spin states have roughly equal probability. So even if we were to drive a Raman process between the two spin states, because this isn't directional, it induces a rate from up to down at the same rate that it goes from down to up, we wouldn't see any population transfer, or we'd see very small population transfer anyway, and it'd be difficult to detect. So what we do instead is we start all of our Raman experiments with one measurement pulse that we then post-select on being in the up state. So in this way, we can imagine pretty much starting with the quasi-particle in the spin up state. Then we apply a Raman pulse, and finally we check the final state of the system. The two axes here are the frequencies of these two pulses, and then the color is the probability of finding the quasi-particle in the spin down state. So you can see that it's mainly dark, and this makes sense. Basically, we're starting in the spin up state, and so this is just showing most of the time we're unlikely at the end of the sequence to find our quasi-particle in the spin up state, or sorry, in the spin down state. It's low probability. But along the diagonal here, we have this feature, and this is due to a Raman process. So the reason it's along the diagonal is that, so this is actually a line of slope 1 that it's following along. And the reason is that if you imagine increasing the frequency of F up slightly, then F down also has to increase by the same amount in order to compensate and make sure that we're still in resonance with this virtual level that I'm showing with the black dashed line. So we can get a better idea of what's going on in this process by looking at the full IQ histogram instead of just the probability of being in the spin down state. And so we're going to do this for two regions of this plot, one off of resonance in black. And here you can see that we're mainly going to find the quasi-particle in the spin up state. So this is again just showing that our post-selection is working. We're starting in the spin up state and then off of resonance. Not much happens, the quasi-particle stays in the spin up state. On resonance though, we see that there's significant population transfer to the spin down state. And this is what we're trying to do with the Raman process. We're trying to drive population from one spin state to the other. There's also a slightly heightened ground state population, and this is due to drive-induced quasi-particle evacuation. Basically, when we hit the system too hard, sometimes we pop the quasi-particle out of the junction. We can drive this process, but we also want to make sure it's coherent. We need it to be coherent if we want to realize a qubit. And so to do that, we're going to run a very similar experiment to what I'm showing here in this pulse sequence, but instead of varying the frequencies, we're going to park on resonance and then vary the amplitudes. So that's what I'm showing here. These amplitudes, A up and A down, you can think of them as just scale factors that multiply the overall pulse envelopes here. And so now the color is the difference between the spin state probabilities. Along the zeros of both these amplitudes, you can see that we're more likely to be in the spin up state. And so this is again just showing that When the drive is off, when the amplitudes are 0, we're mainly going to remain in the spin-up state. But as the driver is increased away from 0, so this is along all the diagonals, we see these coherent oscillations with increasing drive amplitude. So this is showing that we can coherently manipulate the spin of a quasi-particle. To make sure we knew what we were doing, we simulated the system and Q-tip and then fit it to the data. So that's what I'm showing here. The simulation includes readout and dephasing errors. And then the free parameters are the matrix elements between these of these transitions, as well as actually to the other upper double level. We included that as well. And then also a detuning from the Raman resonance condition. That's the small delta here. But the main point is that in general, we have a decent understanding of what's going on with these coherent oscillations, and this is the shape that we expect. Once we'd shown coherence, we wanted to check how long it lasted. So we performed a Ramsey sequence and a Hahn echo sequence to probe the coherence time, and we found 16 nanoseconds and 50 nanoseconds respectively. And then we wanted to know, of course, what was limiting us to these values. So we're not completely sure, but we have a couple clues. So first off, one thing we were surprised by was that there's no dependence on gate voltage or flux. And in particular, there was no increase in the coherence times as we sat on a sweet spot in these parameters at a local maximum or minimum in gate voltage or flux. So this was telling us that electrostatic noise or flux noise wasn't causing these coherence times. The second clue has to do with spinless pair transitions. So I don't have time to go into exactly what these are right now. They were talked about in the last talk quite a bit. But the main point is that the pair transitions should not care about things that couple to spin. And the fact that they're about an order of magnitude longer tells us that the Andreev spin qubit is likely limited by something that couples to spin. So they're this is a well-studied problem in the spin qubit community. Potential options are nuclei, paramagnetic impurities, phonons, and spin orbit coupling. Personally, I think nuclei is probably out because the dynamics associated with the nuclei are normally quite slow. So you'd expect to be able to echo the noise out more, and which we can't really do. So this is a bit of a mystery, but we do think it's something that couples to spin. We could also look at the lifetime of the Andreev spin qubit, and this is limited by two processes, which we probed in a quantum jump experiment. So we can look at parity jumps. These are the jumps between the ground state and the two spin states. And these are summarized by the time scale that we call the parity lifetime. This was like 60 microseconds. This is pretty similar to what we've seen in the past. But there's a second kind of jump that we can now probe directly because we have spin readout. That's just spin flips. So the spin lifetime we found to be 50 microseconds, but we found that it varied with field and a small magnetic field applied perpendicular to the nanowire and flux. So field on the y-axis, flux on the x-axis, and then color is spin lifetime, darker being larger. We can't measure the lifetime in the middle here in this gray region because the spin blobs overlap too much and we can't perform the quantum jumps experiment. But in general, the trend that we observe is that in phase, for instance, as you go closer to zero phase, the spin lifetime drops. And then this pattern kind of shifts back and forth with this small magnetic field that we can apply. And we found that this was correlated with the spin splitting, so the energy difference between the spin up and spin down states. So this plot down here was generated using a combination of its spectroscopy and some interpolation. But the correspondence between these two plots is telling us that we have this correlation that as the spin lifetime, as the spin splitting goes up, the spin lifetime also goes up. So we can again compare to the spin qubit community. And so we have in our system this trend of the energy going up and the spin lifetime going up as well. And then the most natural thing to compare it to would be a single spin qubit. But they actually observe the opposite trend. The spin lifetime goes down as the energy goes up. And the reason for this is that the phonon density of states that the spin lifetime is due to increases at higher spin splitting. So there's just more modes for the energy to get dumped into. So this doesn't work. Perhaps this is just because single spin qubits are operated at much higher energy scales. We're working in the sub-gigahertz regime, and these things are typically operated at many gigahertz. So then we compared to singlet triplet qubits. In the greater than 1 gigahertz regime, these qubits also see that the spin lifetime goes down with increasing splitting. This is again due to phonons. But at sub-gigahertz splittings, the spin lifetime goes up, as in our system, and this is attributed to nuclei. So at first glance, this seems like maybe what's going on in our system, but this is a bit confusing because the reason this is happening with nuclei is that the two electrons that make up the singlet triplet qubit are experiencing different nuclear fields. And we only have one spin, so it's difficult to see exactly how this mechanism will work in our system. So this is also still a bit of a mystery. Yeah, that brings me to my conclusions. I showed you that we can coherently manipulate a quasi-particle spin using Raman transitions, and that we have thus realized the Andreev spin qubit, and that our T2 is 50 nanoseconds, limited by a spinful bath, and then our spin lifetime is quite a bit longer at 50 microseconds, but decreases with the spin splitting. Thank you.
Thanks a lot, Max. So you have left everybody impressed by this skill for improvisation. but this is probably, well, you have, this is a good rehearsal for your thesis, I suppose.
Yeah.
So let's go for one or two questions. I mean, we have now some five minutes left, I think. So either in the chat or raise your hand. Ramon, you check?
Yeah, there are no questions in the chat, I think.
There is
a previous question that we can now, let me see. There was a question, let me try to find it, from Cyril. If you can show the spectrum on a broader frequency window. This was from the previous talk.
Yeah,
yeah.
I think.
We do have the data, but I don't have it on hand. But it's there, so there you can see some data over a wider frequency range in our Nature Physics paper, and then I'm almost done writing my thesis, which will be publicly available soon, and there's plenty of spectroscopy in that, but nothing on hand.
So maybe I can start with a question. So what are the prospects for using these techniques for extracting the lifetimes and the T2 times and so on? If you go actually to the to the topological regime and try to construct a topological qubit out of these nanowires, the same techniques, yeah, or this?
It's definitely a possibility. It's something we're thinking about. Yeah. So in principle, all we have to do is apply a magnetic field along the nanowire. That comes with some challenges. There have recently been some circuit QED experiments done in high field, which is impressive. It can be, and there's yeah.
There's a problem with the sound, huh?
Yeah.
Max, we don't hear you now.
Oh, can you hear me?
Yes, okay. Yeah. Can you repeat the last part?
Yeah, I was just saying that it's definitely a possibility, but there are various experimental challenges, but they have been overcome, for instance, after magnetic fielding. But it's been demonstrated that this is a possibility. So yeah, we definitely look forward to trying to do such experiments.
Okay.
Ramon.
Yes.
You have the topological, you have to cover the whole wire. It will not work in a Josephson junction, right?
Right. This is why I was asking. I mean, if they have thought about it or not.
Yeah. So you actually can
somehow to cover the whole wire. It's not
you don't have to cover the whole wire necessarily. So the idea would be that you can. So we have two segments. So it would be a topological junction. You can apply a magnetic field along the nanowire, and then both sections would hopefully be driven into a topological regime.
I think
Yeah, if
And
both topological, it would work, yeah.
Yeah, you can see in the Andreev spectrum, basically you would, the lowest energy Andreev level would switch parity at some point during the flux bias, and you could hopefully probe that.
Yeah, that would happen, but we'll not have isolated Majorana.
True, yeah, that's true.
So there are no more questions.
I think there are no more questions.
So maybe before we end the session, if everybody can turn on their cameras and go to gallery view, and you just take a screenshot of the screen, and we have like a conference picture. This is the closest we can have for a conference.
Wow.
And then please send these pictures, because we cannot fit everybody in the same picture. So maybe we have a few copies of this kind of pictures. It would be fun. So
you have to turn on the camera.
We are all with cameras now.
Mm-hmm.
Okay, just do it.
Well, there's people still without.
Please.
Edu.
Edu.
Christian. Okay. Ugh. Where are you? Okay, and Ramon, about this afternoon?
Yes.
Would you like to say something?
Yeah, please. So if the idea is that we will have these pre-recorded talks and posters, and the idea is that we will have different separate rooms within the session to discuss with people, and I will allow everybody to share their screens. So please have your slides available, and you will be able to discuss your talk or your poster, to share slides. Let's try to do this as lively as possible, given the circumstances. And let's see how it works. I mean, we are kind of improvising here a poster session or a discussion session. But I think these rooms work pretty nicely. We have checked, and it's very easy to move from room to room. We will name different rooms with different names of the presenters. So, or even people that have given talks this morning can have their own discussion place. So let's try to do it with as much as people as possible. Okay. Okay.
So let's thanks all the speakers in this morning session. And
yeah, and see you this afternoon at 5 p.m.
Thank you. See you this afternoon.
See you. Bye.
Bye. Bye.